And we'll get set up for the slideshow when we get back to it. But let's just go over quickly how things are going to work today. Okay? We're going to finish the lab we started last time. We didn't have much more to go, but we'll finish that. Then we'll get back to chapter 15. And I doubt if we'll finish 15 today, so we'll just carry 15 all the way until 5:15, okay? And at 5:15, we'll stop and have the test on chapter 14. We can have a break in there or whatever also. But any questions on anything so far? Yes? Okay. Can you come in early on Thursday and take it? Do you?
I get out of class at
9:15?
9:15?
Yeah. Okay. Well, I will be in here teaching until 12:15, but if you want to come any time between 12:15 and I don't think it'll take you a half hour, so 12:15, 12:30, even as late as 12:45. You could probably still take it any time then. I'll be down in my office. I'll be here until 12:15, and till 12:15 down in my office after that. Okay, will that be okay?
Yes.
All right. Yes.
You said, did you say that the back of the textbook, at the end of each chapter, you said we could look at the questions?
Okay, I'll say that. Yeah. At the end of the chapter, is that right? Is that what you were saying?
Yeah, the questions in the back. We can look at those and study those, even though they won't be exactly.
Right. Yeah. Those are a great things to study for the test. Yeah. Yes.
How does the test go?
Yes. On chapter 14. I announced it last time. The last 30 minutes will be the chapter 14 test. And remember what you can bring with you for every test. Yeah, anything you want to write on a piece of paper. So you got a few hours to kill. If you want to be writing notes, you can do, while you're after class. It's not optimal, but you can be doing that. So have anything you want to write on a piece of paper, you can have that with you during the test. Can't have the book, okay, but anything you want to write on a piece of paper. Okay? Okay. And as soon as, when we finish a chapter, the next class period, the last 30 minutes, we'll have a test on that chapter. Okay? Now, y'all all got your labs? Okay, I thought y'all decided y'all talked about wanting to do this first, right?
Yeah.
Okay. So let's wrap up the lab. Remind me, I think we answered on page 365, I think we answered 10, 11, and 12 there, right?
Right.
Okay. So I believe we're on, and by the way, we had already filled out the tables, 47, 1, 2, and 3, when we were doing the earlier problems, right? So we're now on number 13, right? Is that where everybody is? Okay. All right. Eratosthenes, I think is how you pronounce that, who lived in the 2nd century BC, okay, was a Renaissance man before his time. Renaissance is usually associated with what, the 1500s or something like that. AD, he was 2nd century BC. He was an astronomer, a geographer, a historian, a mathematician, and a poet, okay? With such a diverse background, it's not surprising that he was the director of the Great Library of Alexandria. Anyone know where Alexandria is? Egypt, yes. One of the, maybe not oldest cities in Egypt, but certainly one of the most famous. Cairo, the capital, is on the Nile. This is on the Mediterranean. There's Alexandria. And best known for the huge university there and the incredible library for that time. For those times, it was an incredible library that was there. Okay. In one of the scrolls at the library, Aristophanes read that at noon on June the 21st, in the southern frontier outpost of Syene, Egypt. Okay? Now, they don't list Syene here, but here's Egypt. And it said, I haven't found it on here. No, it doesn't have it on here. But southernmost outpost of Syene, Egypt, near the first cataract of the Nile. Well, here's the Nile River. It flows down. Actually, it flows north. From the few rivers, it flows almost due north. Actually starts way down here in, I can't remember if it actually starts at Lake Victoria, but it's on the other side of the mountains, I think, from Lake Victoria. And it goes north. One of the longest rivers in the world. Okay. But near the first cataract of the Nile, obelisks cast no shadows. At noon on June 21st, the obelisk cast no shadows. You know what an obelisk is, right?
No.
It's what? No. You know what the Washington Monument is? Yeah, that's an obelisk. It's one single structure going very tall, not much to it anywhere else, but yeah, it may have some carvings and other things on it. That's an obelisk. Okay? As noon approached, the shadows of the temple columns grew shorter and shorter and shorter until at noon they were gone. Reportedly, a reflection of the sun could be seen at the bottom of a well. You can see the sun directly overhead if you look at the reflection at the bottom of a well. On June 21st at Syene, the sun was directly overhead. Get the idea? Now, what do you think the latitude of Syene, Egypt was? Okay. Sorry, I forgot. Let me get out of that for just a moment. I forgot we use this in lab. I should have left this up from this morning's class. Okay. All right. Here we are in, let me get my pen reactivated. We don't know where we are at Syene, Egypt, but here we are in Syene, Egypt, standing here. Here is our horizon here. Here's our celestial sphere here. Okay? And we know that the sun is right up here. Here's the sun. Directly overhead on June 21st. Directly overhead on June 21st. Now, what is the declination of the sun on June 21st? Anyone remember? 23.5 degrees, north or south? North. Okay. And, by the way, here's unhealed. I can find you. There you are. So right now we're only missing Fred and Sam, right? So leave everybody else is here. We're continuing on the lab. We should finish it up fairly quickly here on number 13. And there is Fred, right? Okay. Now we're just missing Sam. Now we haven't seen Kendrick Deontay Williams. Does anyone know him? He's not here today, right? Okay. So we're just missing Sam. We're doing question 13 on the lab for chapter 14, page 366 of the lab. And by the way, it seemed like some other people weren't aware, we are having a test on chapter 14 the last 30 minutes today, right? Okay. And you can have with you on the test, on every test, a piece of paper with anything written on it you want to. Okay?
On one sheet.
On one sheet, yes. Yeah. Okay. Now, the question here, what is the latitude at Syene, Egypt? We know from what they told us in the problem, in the lead up to it, the sun is directly overhead on June 21st, and y'all just told me that the sun is at 23.5 degrees north on June 21st. Okay? Now what is that north of? The equator. So that means the equator must be here. Okay? Here is directly overhead. So this would be 23, this is celestial equator, 23 degrees 30 minutes. Okay? So what's the latitude of where you are? Say again?
6730?
Second?
6730?
No, it's the same. This angle here, there's the Earth's equator. You must be 2330. What is 2330 north? Anyone know a name for it? What? No, the axis is here. 23.5 degrees north of the equator. That's a little dotted line there. I don't know what that means. Say again? There it is. Tropic of Cancer. Capricorn is 23.5 degrees south of the equator. Tropic of Capricorn. So Syene, Egypt is on the Tropic of Capricorn, out of Cancer, which is, and it must be at that time, Egypt. This isn't quite the southernmost part of Egypt, but it must have been there. And by the way, it's pretty close to where, and this would have made sense where you put one of these, the first cataract of the Nile. That's one of the places where you sort of have a waterfallish type thing. That's where they put the Aswan Dam. That was the dam they built, hydroelectric dam they built on the Nile River to provide energy for Egypt. Egypt, one of the Middle Eastern countries that has no oil reserve. So they had to import most of their fuel. They decided to dam the Nile and try to and put in hydroelectric plant there. And sounds like a great idea, right? Except it messed up the slow downstream some partly, and they didn't have nearly the flooding they used to. That sounds like a good idea, doesn't it? Except that now they didn't have deposits from up there coming down, refertilizing the valleys, and the crops fell off. So, yeah, we do all sorts of things that look like good ideas, and sometimes they don't turn out being quite as good as we thought. So anyway, everybody see that your latitude is the same as the distance the sun is above.
So the answer is 23.
What's that?
The answer is
23.5 degrees or 23 degrees 30 minutes north. You have latitude north-south. That's north of the celestial equator. I mean of the equator. So that would be north. All right. It says readjust the celestial globe. I'm going to draw it here for our latitude. What is our latitude? Second, 33 degrees, 23 minutes, 45 seconds. You got it. Not going to be a lot different from what that was, but pretty similar. Okay. Can't get my pen to activate. There it goes. All right. So that's going to be a little over a third of the way down. This will be celestial equator. The real equator is here. This is 33 degrees, 23 minutes, 45 seconds. Bessemer, Alabama. So this is 33 degrees, 23 minutes, 45 seconds. Okay. Question here. At what declinations, those are declinations measured from where? From what? North of what?
The equator.
The celestial equator. That's the declination. What range of declinations can stars have so that they never set? That is, they are always above the horizon. Okay? Now, where would that be? Here's our horizon. What star in particular do we know never sets? The North Star. Okay? It's probably not exact here, but here is good old North Star or Polaris. Okay? We know it never sets. So basically the stars all around here in this range never set because they go around the North Star. Okay? Well, my line is pretty lousy here. Let me see if I can clean that up a little bit better. Let me clear those out too. Okay. And we've already established, remember when we did this, that this angle here is what? What's that? This angle right here. This is our latitude, 33. Remember, the North Star is always your latitude above the northern horizon. Yeah.
Wait, I'm sorry, I'm confused. What was the answer for the question you're speaking?
What's the question?
23 degrees and 30.
What is declination? Wait.
Thank you.
Oh, what is our latitude?
Oh, no, we did.
Okay, I
We got it.
Got it. Okay. I don't hear well, sorry. Okay. Now, remember, this is the very first problem we did, showing that the altitude of the North Star over the northern horizon is the same as your latitude. So, that means all the stars in this region here never set, right? So what would be the declination of those stars? Okay, well, you would go, the North Star declination is 90 degrees, right? So it'd be something up to 90, okay? Now, this angle here we know is 33 degrees, 23 minutes, 45 seconds, right? We already established that. Your latitude, the North Star's altitude over the northern horizon is the same as your latitude everywhere, okay? Where we are, okay? So this span, 33 degrees, 23, 45, on this side of this would be the minimum declination up to 90 degrees. So any stars between that and here. So basically what we've got to do is subtract this from 90, because this is 90 degree declination. The North Star has a declination of 90 degrees above the celestial equator. So let's write 90, but not write it as 90. How would we write that? 89 degrees, 59 minutes, 60 seconds. 60 seconds is 1 minute. That would give you 60 minutes. 60 minutes is 1 degree. That would give you 90 degrees. Okay? And let's subtract from that the 33 degrees, 23 minutes, 45 seconds. And what do you get? Where are you starting here? 50 what? 56 degrees, 36 minutes, 15 seconds. So from there to 90, this to 90 degrees. That would be the declination of the stars that never set on from where we live. Further north, if you were further north here, this would be further north there, that would be there, you'd have a wider range. Okay? Stars that never set. Does that make sense? Okay. All right. Now, unfortunately, I don't have current data on Mercury and Venus. But the last time I went to Birmingham Southern Planetarium, she gave me a thing, and this is for an earlier year, and it may not be current, but we'll use this and pretend it's us now. Okay? And let's see, we don't have August here, but it has September. We'll go on September. Okay? Venus, it says, the question here is, your instructor will provide you with coordinates of Venus and Mercury and Venus on the day of this lab session. I don't have that. On the mark, and we don't have one of these globes either. Okay, so locate the sun for today. Okay. Number 15. Forget about what's worded at the bottom of the page. Just do this. When is Mercury visible in a dark sky? Okay. Now your two options are just after sunset or just before sunrise. Those are the only two options you have for Mercury. Mercury is so close to the sun that when the sun's coming up, the only time you have a chance of seeing Mercury is just before the sun comes up. If Mercury's on the top half of its orbit, you may be able to see it then. Or just after the sun is set, if Mercury's on lagging the sun, you may see it then. So it's one of those two. Well, let's see what it says for September. It says Mars and Mercury are lost in the glow of the setting sun. Okay? So that will be just after sunset. I mean, just barely after sunset. In fact, you'll probably never see it because it's lost in the glow. The sun goes down and Mercury is just behind it. So, fat chance of seeing that. Okay? Number 16, when is Venus visible on a dark sky? And we'll use September again here. It says it's low at dawn on the east-southeastern horizon. So guess where it is? At dawn, just before sunrise. So on the Venus would be the morning star. Now this was for this year. I don't know if it's the same now. Probably isn't exactly the same, but we'll use these data just in case that's what we got. All right. Now, the question. Estimate how long each is visible in the dark sky. And guess what? Mercury is always, if you can see it at all, guess how long? Very short. Just a number of minutes. You'll never see Mercury more than just a few minutes. I don't believe it'll ever be as much as an hour. It'll just be a few minutes, either just before sunrise or just after sunset, and we've said just before sunrise. No, I said set. Just after sunrise. Set. What's that? Just a few minutes. That's all you have to put. In fact, the odds are you'll never see it. I'm not sure I've ever seen Mercury. I mean, I usually am not looking that close to the horizon when the sun rises or sets because you don't want to look at the sun directly. You've got to look just either right after it goes down or just before it comes up and hope you can maybe see something there that possibly is Mercury. Okay, how about Venus? Well, Venus is farther from the sun, So there are times when it will lag or lead a little bit longer, and the indication here is it's low at dawn, so probably no more than an hour. At most, it would be just a few hours, but the way they describe it here, it would be less than an hour, it sounds like. And again, the reason is okay, I think Hunter is going to be the sun for us today. You're pretty bright, aren't you? Okay. Because Mercury and Venus are very close to the sun, when the sun comes up, Mercury and Venus is somewhat close to it. Mercury even closer than Venus. Venus may lead it a little bit or lag it a little bit. Or after the sun goes down, it's just catch it. Mercury, only for a few minutes after the sun comes up. After the sun sets or before the sun comes up. Venus, you can see it maybe as much as an hour or a little bit more. That's why it's called the evening star or the morning star. It's bright. It's the brightest star out there. It's not a star, it's a planet out there other than the sun and the moon. And it's very bright. Usually the first one you'll see or the last one you'll see, last in the morning, first in the evening, because it's so bright, but it'll always be near where the sun. Like it said here, it said low at dawn in the east-southeastern horizon. The sun rises in the east, Venus is going to be rising in the east just before the sun does. Okay. Any questions? All right. That finishes the lab. Technically, you have at least a week. If there's any part you didn't get and you want to listen to the YouTube videos or whatever for that. And by the way, I did want to say this. Remember, the YouTube videos are out there. I don't have them, the link set up in Blackboard yet, but you know how to locate things on YouTube. You can go and look for PHS111. You can look for my name and pick the files that are out there, the recordings that are out there that were done in the last couple of weeks, last week and this week. That will be it. So even though the PowerPoints aren't there, everything in that chapter, plus me talking about it, is out there on that YouTube video. Okay, so those may be good things to study too if you find those helpful. All right. So if you're finished with it and want to turn it in today, you can. If you want to keep working on it, please get it in within a week from today. Okay? Sooner the better, but get it in whenever you can. Now, I do want to mention this. In my second class today, I got my first paper in for the term. So somebody's already turning in a research paper. So it can be done.
Everything about it.
What's that?
I went to look for the syllabus to tell me a little bit more about the paper because I wasn't completely with you on that first day. So.
Okay. Yeah. Well, it's all out there on YouTube.
Oh,
Everything's on YouTube. Okay.
All right.
Yeah. And I'll get it out there on the Blackboard as soon as I can. But that's pretty static. But it's up there. Everything I'm saying about it is out there on the YouTube video. Okay. They're coming in droves now. Okay. All right. And please try to get them in within a week so I can get them back to you shortly thereafter. All right, if no more questions on Chapter 14, anything as you were studying this weekend, did you run into questions on Chapter 14? Anything you weren't able to figure out? You saw? What's that? I don't hear well. So.
Oh, I'm sorry. No, I was talking about the test.
Talking about what?
The test.
The test. What about it? Yeah. Okay. Any questions, feel free to ask. Well, I'm going to go on and get rid of this PowerPoint if no one needs it any longer. Okay. Then close that out, and we'll open this back up. All right. I think this is where we got last time. What's that? This is 15. Okay? And 15 and 14 are pretty closely related, so you might see some stuff here that will refresh things in your mind from 14 as well. Okay. We got just a few slides done. It doesn't indicate which slide this is, but when we got started here. Let's look at, we're still in 15.1, planets, dwarf planets, moons, and other bodies in the solar system. Well, the solar system, what's the central part of the solar system? The sun, good old Sol. It's Sol system, solar system. Okay? Now, the sun, there's a statement in the book, and I want you to be aware of it. All right? Well, we're not quite there yet. There we are. It's on page 379 if you got the current text. Okay? It's the beginning of the very last paragraph on that page. The sun has 700 times the mass of all the planets, all the moons, and all the minor members. That's the comets, the asteroids, the meteors, everything in the solar system. The sun has 700 times the mass of all those others put together. So guess what's the biggest kid on the block? The sun, by far. Jupiter, as big as it is minuscule compared to the sun. Now later in this PowerPoint show, we may get to it today or may not, you'll see something said about the comets containing more mass than any other thing in the solar system. They don't mean the sun. The sun is 700 times everything put together. All right, now, we know we have 8 planets. We used to think we had 9 when we counted Pluto a planet. We have changed that and made Pluto a dwarf planet. Okay? So we have 8 planets we know of. Has anyone been following the discussions about the possible 9th planet?
They found 9 more.
What's that?
Probably 9 more than they found in some other constellation. About 100 light years away.
Okay, I can't quite hear it, but they think there's a 9th one out there. Is that what you're saying?
It was more. I think they found 9 more planets. NASA did.
Really?
Yes.
9 more than the 8 we know of now?
Yes.
Okay, that's hypothesized, okay? Oh, you mean outside of our solar system?
Yes.
Oh, okay, yeah. Okay, they have detected planets on other stars. They're really hard to detect because they're so tiny and they don't give off light of their own, but there is actually what they think a 9th planet in our solar system, or at least some people think that, just because of gravitational effects and things like this, we haven't seen it yet. Well, guess what? None of us have seen Pluto. None of us have probably ever seen Neptune or Uranus. They're so stinking far away. You have to have a very, very powerful telescope to see them. So far, this 9th planet, if it exists, and many think it does, is probably on the other side of the sun now, but it's moving so slowly that we haven't detected it at all, okay? And it's so far away. So, for now, we're just going to say 8 planets. Approximately 100 moons, okay? Not real clear because if you think that defining planets and dwarf planets are tough, define what's a moon and not a moon, that's even more of an issue. Actually, I would say Jupiter has, if not the majority, the huge plurality of the moons. It seems like it does have in the 50s. but it may be in the 40s of moons. Saturn is next, and then Uranus and Neptune are next, and then we have the other, have very few. All right? Thousands of asteroids. Now, where are the asteroids?
In a belt.
The asteroid belt. Yeah, they live in their own belt. And where is that belt located?
Between Saturn.
No, between Mars and Jupiter. Okay, between Mars and Jupiter is that belt of little bitty bodies, okay, called asteroids. And then there's millions of these icy bodies out there that are sometimes become comets, okay, and sometimes just hang around out there and never go around very much. And there's lots of other stuff out there too. Pretty small, fairly insignificant, but a lot of it out there. We measure these things in our solar system in terms of astronomical units, because miles you get so many zeros on the number of miles or kilometers you got. So what they do, they measure in astronomical units. That's the average Earth-Sun distance, which I usually call 93 million miles. Okay? They say 1.5 times 10 to the 8 kilometers. Okay? By the way, 93 million would be 9.3 times 10 to the 7th miles. This is 1.5 times 10 to the 8 kilometers. That's about the difference there. Okay? Let's think of the planets now. How do we classify these? Several ways. One is size, how small or how big they are. Another is density, how dense or how light they are. Okay? And another is what kind of atmosphere or not do they have. Okay, we'll talk about all three of those separately for each planet. But the first classification we do is somewhat size, somewhat density, and somewhat atmosphere. A little bit, not so much atmosphere. Is what type of planet are they? Okay? And basically those inside the asteroid belt are what we call terrestrial planets, meaning they're rocks. Okay? Third rock from the sun. I don't know if y'all remember that. Mercury, Venus, Earth, and Mars are the 4 terrestrial planets. Mostly rocky materials. Largely metallic nickel and iron. More so iron than nickel, but largely nickel and iron. Now, most of the time, I'm not sure exactly why this is the case. Nickel is usually deeper inside the planet. Iron is scattered throughout the planet. It's mostly deep inside, but you get it throughout. Those are the terrestrial planets. Mercury, Venus, Earth, and Mars. Mercury, solid rock, pretty much. I mean, it may have a molten rock core, but it's not. Venus, mostly solid rock, but it's got a very thick, dense atmosphere. And here we have Sol. Okay? Sam, I'm sorry. Solomon, Sam. Okay. I was thinking sun. Okay, I think everybody's here who's been here, right? The only person we're missing is the person who's never been here, Kedrick Deontay Williams. So I guess he's probably not going to be here. Now, just a reminder, the last 30 minutes of today, from 5:15 until you finish, is going to be the test in chapter 14. Okay? And you can have with you a sheet of paper with anything you want to write on that sheet of paper from chapter 14. So those are the innermost planets. Now, why did I say their size? These are the smallest 4 planets by far. Okay? Density. They're smallest, but they're also the densest 4 planets by far. Okay? Atmosphere, kind of hard to say. Mercury has basically no atmosphere. not much anyway. Venus has an enormously thick, dense atmosphere. Earth has just the perfect atmosphere. Okay, Mercury too thin, Venus too thick. Ours is just right, Goldilocks. Okay. Mars has a very thin atmosphere. It has one, but not very much. Okay. The main thing that makes what makes them dense, mostly rocky materials, solid materials, metallic, nickel, and iron predominant. So therefore, they're pretty dense and but small in size. May or may not have atmosphere. Then outside the asteroid belt, you have the giant planets. Now, quite often they're called gas giants. Okay. And what they mean, they're not made up mostly of rocky materials, they're made up mostly of gases. Okay? That's Jupiter, Saturn, Uranus, and Neptune. Mostly hydrogen, helium, and methane. That's about all, folks. I mean, you got other things there, but not so much. Hydrogen, helium, and methane. Hydrogen, helium. What else is made mostly of hydrogen and helium? The sun. Well, hydrogen Mars, but the sun. Okay? The sun, and because it's one big nuclear reaction. Okay? It's, I want to say about half hydrogen, half helium. It's probably a little more hydrogen than helium, but that's what's fusing is the hydrogen and it becomes helium. Methane. Anyone know what methane is? Say again? It's a gas. We won't talk about sources or whatever. But methane is CH4. Carbon in the middle and 4 hydrogens around it. Okay? That's methane gas. Okay? It is a gas, often referred to as a greenhouse gas, because of the carbon mostly that's there. It's in our planet, there's a fair amount of methane, not a whole lot. It's a very minor amount of our atmosphere. But there are 2 really major sources of that methane. I'm not sure the first one is that major, but people gripe about it is these feeder lots with cattle and things like this. So most animals produce methane in their flatulence, you know. Okay. Including animals that walk on 2 legs. Okay. So, but another source is termites.
Termites.
Yes, termites, especially in the tropics, where you have the tropical rainforest and all these limbs and trees and stuff lying around. Termites are a major part of that ecosystem, and they're consuming this complex carbohydrate we call wood, cellulose, and that's a difficult thing to digest, but termites are able to do that, but they produce a lot of methane in doing that. They have a lot of flatulence, and actually there's enough of them and enough source there and stuff, they produce a lot of methane in our atmosphere. Well, guess what? These gas giants don't have any cattle or termites, either one. So the interesting thing to me is where is that methane coming from? Well, remember Lucy in the Sky with Diamonds? At the end of most stars' life, they turn into a black chunk of carbon. Okay? And that carbon, if it's been exposed to much hydrogen, sort of, you might say, burned in hydrogen, then that could have made the methane. So I think of methane as a organic gas, but that methane can't be organic because nothing has lived there. So, pretty interesting. Pluto, no longer considered a planet, but now considered a dwarf planet. And while we're talking about dwarf planets, in that same area that we're talking about, today is in the paragraph, 2 paragraphs above the one I was just referring earlier. Today there are 8 planets. There they are: Mercury, Venus, Earth, Mars, the terrestrial 4, Jupiter, Saturn, Uranus, and Neptune, the gas giant 4. At least 5 dwarf planets. Pluto being the one we know best, Eris, Ceres, and I don't know how to pronounce it. To me, it's Maki Maki. I don't know if that's how you say it or not, and Haumea. Okay? So there are the 5 dwarf planets. I know that Pluto is out there beyond Neptune most of the time. Eris, I think, is out. Let's see, I'm trying to remember. 2 of these are in asteroid belt. I believe that's Eris and Ceres. They're large, large asteroids, so they call them dwarf planets. Maki Maki and Haumea, I can't remember exactly where they are, okay? But any of those could be a potential paper topic, you know. What can you find out about them, you know, properties, characteristics. So anyway, those are the dwarf planets. We have at least 5 that have been identified as dwarf planets now. 8 regular planets, 4 terrestrial, 4 gas giants. All right. Any questions on that? The order of the planets. We've already talked about that to a large extent, but again, this picture kind of drives me crazy, as you have noted. Number 1, the scales. The scales for the planets themselves, they're not bad. Okay? Mercury is fairly small. Venus and Earth are almost the same size. Mars is considerably smaller than either, but bigger than Mercury. Those are your terrestrial planets inside the asteroid belt. There's the asteroid belt. Okay? That's probably where Ceres and Eris live. Okay? Then you have the gas giants. I mean, huge gas giants. Jupiter, Saturn, Uranus, and Neptune. They show Pluto here. It's not a planet, and it sure doesn't behave like that. Okay. What's really wrong about this, what I don't like about it, the scale of the sun to the planet, the sun should be more than 700 times bigger than any of these. But if they did that, you wouldn't see the planets at all, not even the biggest one. Okay? So they just scaled down the sun. Another thing that really bugs me, the distances from the sun are nowhere close to the right scale. I mean, they look like they're fairly uniform. They're not. And the thing that gets me the worst about this is the fact they never line up this way, ever, ever, ever. They're always some other part of their orbit. They're never anything close to this. So that's the other thing. Now, another thing that's sort of good, you have to look to pay attention. Mercury has no moon. Venus has no moon. Earth has a relatively large moon. I think you'll only find like 5 moons bigger than this. There's 4 big ones around Jupiter and at least 1 big one around Saturn. I don't think any of the other planets have a moon close to the size of our moon. And we're this tiny little terrestrial planet, and we have one of the biggest moons. Pretty interesting. Mars has 2 very small moons, and I'm guessing Mars probably ripped them out of the asteroid belt. Okay, at some point they just got too close, and Mars got them in its orbit. I don't know that for a fact. I can almost guarantee you that's what happened with Jupiter. Jupiter is so huge, so massive, it's probably stolen a lot of asteroids and made them its own moons. And we'll talk about those 4 big moons of Jupiter later. Now, Saturn has a lot of moons, but it also has these fantastic rings. What's in those rings? Particles of stuff that are floating around that. Well, what do you classify a moon and what do you classify a ring? Well, these are awfully small. These are pretty good size. That's why I said they just estimate the number of moons. Uranus and Neptune both have quite a few moons. They're almost sister planets. I mean, they're very similar to each other. Okay. All right. But for relative sizes, that's not bad except for the sun. So let's look at these individually. Here we go. In the asteroid belt, one of the innermost asteroids is Ceres, which is not really an asteroid. They classified it a dwarf planet now. So it's between Mars and most of the rest of the asteroid belt. Okay? Pluto is a dwarf planet out there beyond Neptune, as is Haumea, Makemake, and Eris is way out there. I was thinking Eris was in there with Ceres. Their names are just so similar. I thought they were. Eris is way out there. Okay? And you'll see another thing listed in that figure 15.2 in your text. The Kuiper belt objects. Those are basically comet-type materials. Okay? We'll talk about those later. There's an Earthrise over the surface of the moon. You've probably heard of moonrises over the surface of the Earth. There's a picture that the Apollo 11 astronauts took as the Earth was rising over the moon's horizon, which is hard for me to believe, but then on the other hand, it's not that much. There are people out there who think the whole visiting the moon and being on the moon was a hoax, that we've never done it. It just is a mystery. The reason I know, we were at some sort of a family event, I believe it was a wedding or something like that, and on Karen's side of the family, my wife's side of the family, one of her brother's children, that was either a wedding or a graduation, and we were out there on her brother's wife's side of the family, a brother-in-law to my sister-in-law. He was telling us how, yeah, they didn't really go to the moon. Here he is talking to my father-in-law who worked for NASA, okay? He was sending up some of the experiments they did, and this guy was telling us, not realizing that, no, we didn't even go there. It's all a hoax. And it's just unbelievable to me that people in America today could still believe that. Okay?
A lot of people still think the Earth's flat.
Yeah, I think there probably are some. Unbelievable. Okay. What's that?
It's the same people that believe that we didn't go to the moon. They're like, Earth's flat and we didn't go to the moon.
Right, yeah. Amazing. There is an example 15.1. How long would it take to travel the average distance between the sun and Earth at a typical jet airline speed of 1,000 kilometers per hour using the equations from section 2.2? Of course, the equation section 2.2, that was part of the book we haven't had, didn't study. If you wanted to look into that, it would be, they talk about the solution. It's amazing, the time that we're talking about. Interplanetary space probes travel about 7.3 kilometers per second, which is awfully fast, okay? How far could it travel in a year? And it gives there the number of kilometers, and you haven't begun to get close to the distance between the Earth and the Sun. It's just amazing. Now, the other thing I want to talk about before we start on Mercury is the table at the top of page 381. This table has the most incredible amount of data in it, and it's all really interesting. Well, maybe most of it, I'll say, is really interesting. Okay? We will be referring to this as we talk about each planet and the really key and interesting pieces of that data. So, well worth taking a look at. It's so much, it's overwhelming, but try to pay attention to it. Mercury, as we said, is the innermost planet. Now remember, we're going to refer to everything in an astronomical unit. Tell me what an astronomical unit is. Distance between the Earth and the Sun. 1 astronomical unit. That distance. Okay. Now Mercury has what they call a highly elliptical orbit. And it's mostly you sense that or see it because it's the closest thing to the sun. So anything that's not circular is going to really be exaggerated there. What do we mean by elliptical orbit as opposed to circular orbit? A circular orbit is perfectly circular, around, perfectly round. An elliptical orbit has a little bit of kind of an egg shape to it. One axis is longer than the other axis. Okay? Now, that's not quite the best description of it. Here would be a highly elliptical orbit for the Earth. The Earth doesn't have this, but it could work. Are you going to read the song for me again? You do it so well. Okay. So, a highly elliptical orbit, we would be this far from the sun at one point. At another point, we might be here, and then another point will be there. An elliptical orbit has a closest point and a farthest point. Mercury has one of the highest elliptical orbits. Okay. Now, of the planets, if you included Pluto, even though Pluto used to be considered the farthest planet out, it had a far more elliptical orbit than even Mercury does. I mean, just magnitudes greater. In fact, we say Pluto was outside Neptune. On average, it was outside Neptune. There were some times in its flight it was inside Neptune, between Neptune and the sun. Other times it was way, way out there. Highly elliptical orbit. Okay? More so than Mercury. So that's why one of the reasons they threw out Pluto. But Mercury is more elliptical than most of the other planets, but nowhere close to as much as Pluto was. The average distance from the sun, because it's highly elliptical, sometimes it's closer, sometimes it's farther, is about 4/10 of an astronomical unit. So that means it's closer to the sun than it is to Earth. 6/10 of an astronomical unit from Mercury to us, 4/10 from the sun to Mercury. It is close there, folks. Really, really close. Now, here's another thing rather odd about it, and this is all in that table. The orbital period, that is the time it takes it to go around the sun, is just 3 months. It takes us 12 months, a year. Well, Mercury's year is only 3 months long, you might say. Its trip around the sun takes only 3 months. But look at its rotational period. It turns really slowly. About 2 months. So it turns, it takes 2 months for it to make one spin, 3 months for it to make one thing. So its day is about 2/3 of a year, or something that's of its year. Okay? It's really bizarre. Okay? It's spinning slowly, but moving around the sun pretty rapidly. Okay? It doesn't really matter who. And by the way, as we said before, it's visible shortly after sunset or shortly before sunrise if you can see it at all. Most of the time you're not going to be able to see it. If you ever could see it, it's only going to be very shortly after sunset or very shortly before sunrise. As I said, only a number of minutes, more than likely. Okay. These two things that are said in this bullet basically are repeating each other. Mercury has almost no atmosphere. Okay? Therefore, and by the way, most things in our solar system go around the sun. What things in our solar system have the most elliptical orbits? More so than Pluto. The comets. The comets start way, we haven't talked about them yet, but we're way out there, and then they come in and flip really close to the sun and then go way back out there again. Okay? In that, there is all sorts of other particles, sometimes chunks of things, that are always out there in the atmosphere. Far apart, I mean not in the atmosphere, in the solar system. Way far apart, and every now and then, and it's flying around the sun, Mercury hits them, or they come flying in and hit Mercury. And because it has no atmosphere, they crash on the surface of the planet. When they crash, they form a big crater. So when they say highly cratered, no atmosphere, they're saying the same thing. If there was any atmosphere at all, then they would probably burn up in the atmosphere, or largely burn up, and very few ever hit the thing. But since there is no atmosphere, anything that comes in the path, crash. So it's highly, highly cratered. It is the smallest planet. Back when Pluto was considered a planet, Pluto was much smaller than Mercury. That's the other reason it was kicked out. It was way too small, really, to be considered a planet. But Mercury is a planet, and the smallest of the planets. Were you going to say something, someone? Okay. So here's the illustration of why it's so hard to see Mercury. Wherever the sun is, Mercury is really close to it. Less than half the distance from Earth to the sun, Mercury is in between there. So, when, and this is a gross exaggeration here, the orbit doesn't quite do that directly different, but when Mercury is visible, when you have what we call a full Mercury, that means it's on the other side of the sun, so it's the furthest from us, but it's also sort of closest to being blocked by the sun. So the full Mercury, when it would be the brightest, that's when it's one of the closest to, being obliterated by the sun. Out here, when we're likely to see the most, you have at most half of it illuminated, like a half moon. So there's not much to see. When it's closest to us, we see the dark side of Mercury. We only see a little sliver, so it's hard to see even when it's closest to us and further from the side. So hard to see. Okay, Mercury has phases just like all the terrestrial type bodies will have phases. All right, here is a composite picture of Mercury taken by many different flybys that they've had of Mercury and sent back to Earth, and you can see the craters like crazy. And basically, seeing the craters, you know it doesn't have much of that. It's just been pummeled. Now, by space junk. Now, one thing they don't mention here, but I wanted to point out, I think it's in the text. Let me see if it is in the table. One of these, and let's go back to this picture here. And again, this is somewhat of an exaggeration here. Most of the planets, the sun here, most of the planets, their orbits are all fairly much in the same plane. Okay? Now, this thing that they call inclination to the ecliptic, Mercury has the greatest one of those, that's 7 degrees. Well, if you think 7 degrees is really not very much. This would be 30 degrees. That would be 45, that's 60. So 7 degrees is really small. And it's mostly because it's so close that it's such a big angle. This is way more than 7 degrees. So they exaggerated it some. But because it's close to being flat, we aren't going to see it very frequently. But notice the others here. It's by far the greatest inclination of the ecliptic. The next greatest would be Venus, which is the next closest to the sun. And then you go out, and when you get to Saturn, it's pretty large for being that far away. But anyway, so that's another thing. If you had included Pluto, I don't remember for sure, it seems like it was more than 15 degrees. So it's way out of line with all the other planets there. That's one reason I call it planet. Okay. Now, one thing that's in the text that's not mentioned on the slide, and I hate it when they do this. Of course, Mercury has no moons. We've already said that. It has no atmosphere. And one thing the atmosphere does for us, it sort of acts like a little blanket. Okay? So when heat gets trapped, even at nighttime when we're not in sun, we stay fairly warm. But if you think about it, the nights, especially in the wintertime, that cool off the most, on the clear nights. On the cloudy nights, we don't usually get as cold, okay? And even in the summertime. Last night was relatively clear, and it was 68 when I got up this morning. Pretty nice temperature, okay? So you usually don't have that in August, okay? The dog wanted to go right out, and she laid out all morning until I was almost ready to leave before she came in. She just loves that weather, okay? Now, so therefore Mercury. Would you think it's the hottest planet because it's closest to the sun? You would think. Okay, and actually when it's facing the sun, it is by far the hottest. It is baking. I mean, really, really hot when it's facing the sun. Of course, the side that's away from the sun is frigid because there's no atmosphere to balance things out, to form that blanket. The next closest planet is Venus. Much further from the sun than Mercury is, but it has this really dense atmosphere. So really, you can't tell a difference between day Venus and night Venus as far as temperature. It's so hot. The entire day is hot because so on average, it's hotter than Mercury. When Mercury's facing the sun, sure, it's hotter, but when it's not facing the sun, it is frigidly cold. So its average temperature is actually less than that of Venus. Because those gases in Venus's atmosphere, guess what? Greenhouse gases. They trap that heat like crazy. Carbon dioxide, methane, seems like a fair amount of sulfuric acid. I mean, not a good place to be. They didn't mention this, but that's something else to know about Mercury. All right, so let's move to Venus. Okay, as we said, Mercury is 0.4 AUs. That's not Auburn University, by the way, it's astronomical units. Okay, whereas Venus is 0.7. So that's 7/10 of the distance between the sun and the Earth. There is Venus. So it's not quite twice as far from the sun, but close to it. Close to twice as far from the sun as Mercury is. Not quite that much. Now, Venus is often called our morning and or evening star. It's not a star, but it's the brightest object out there after the sun and the moon. Very brightest out there, when you can see it. Okay? Most of the time, of course, it's closer to the sun than we are. It's going to be, when it rises, it's going to be in the east. Okay, wait. When it's the morning star, it's going to be in the east. When it's the evening star, it's going to be in the west because it's either leading or following the sun. It's always around the sun. So that determines which direction to look for it. Now, it, just like Mercury, we saw the picture, exhibits phases like the moon. A full Venus is when it's on the opposite side of the sun from us. We see it really bright. When it's on the same side of the sun as us, then we only see a sliver of it. It'll be brighter, that sliver will be, but we won't see as much of it. Okay? Here is the strangest thing about Venus. Its rotational motion is opposite that of the orbital motion. All the planets travel around the sun in the same direction. And all but sort of two of them spin the same way. Venus is the one that spins so crazily. Its rotational motion is opposite the orbital motion. But what's even more strange, its day, which is one spin, is longer than its year. Okay? But that's because it spins so terribly slowly. Yes?
No, wait, can we go back to the motion? How does that spin?
How did what?
No, on Venus.
What's that?
On Venus,
Okay, on Venus?
it's rotational motion. Like, so how does it spin? Are you talking about
Okay.
rotation
Here
around
would
the
be-
sun? Or
yeah.
just
Okay, no. when it talks about rotational motion and orbital motion, rotation is spinning on its axis and orbit is moving around the sun. Okay, so let me see if I can get this right. We move around the sun like this when we spin like this, so we're at the same axis. When Venus is moving around the sun, it's moving around the same direction we are, but it's spinning backwards.
Spins backwards.
Yeah.
Okay.
So not only is it spinning backwards, it's spinning very slowly backwards. So it spins one time. It takes longer for it to spin one time than it does to go around the sun one time. Okay? And to get the actual data for that, the Venus's orbital motion in Earth years is 0.62 Earth years. So that's about 5/8 of an Earth year. So that 5/8 of 12 would be 7 months. Okay? Around 7 months. Its rotational period, 273 days. That's well more than 2/3 of a year, okay? So, it's spinning backwards too. So that's why they have the minus sign there, okay? It takes 243 days for it to spin one time, but it's spinning backwards. Now, maybe when we go to the planetarium, he may talk about this. There is some conjecture that probably something hit Venus pretty hard. And now remember, okay, we haven't talked about the formation of the solar system yet, but we talked about the formation of the sun. And when it was in the process of, overcoming gravitational collapse and just beginning the fusion that's blowing things out, it was a messy period. Things were shooting out, coming in, stuff. There was a lot of activity going around. About that same time, the planets were in this, what they call an accretion disk around, and they were sort of forming up. And maybe about the same time they were forming, and so Venus may have gotten hit by some of the other junk that was out there and actually made the spin in the opposite direction. That's a theory. Of course, no one can prove it. There's not enough evidence to say it did happen. And that has been visited by numerous probes. Okay? It's our closest neighbor of the planet. The moon is actually closer. It's mostly carbon dioxide atmosphere, which I find really interesting. You think of carbon dioxide as being breathed out by living things? That's not where this carbon dioxide came from. It came from the heating up of carbon, which is all over, when you have stars forming and stuff. Very, very high temperatures because of that dense atmosphere, but also because of the dense atmosphere, very high pressure. You would not want to live on Venus, okay? It would crush you. You would gag it immediately because it's no oxygen, carbon dioxide. You'd be toast, you'd be boiled to death. It would be extraordinarily hot and really inhospitable. Lots of acid, as in sulfuric acid, carbonic acid, just not a good place to be. The surface is mostly flat, but does have mountains. It has volcanoes. It probably is not that much different from the surface of the Earth, minus the oceans and stuff, because it wouldn't have that. That would all be evaporated if they had any water. But it's mostly flat, but it does have mountain ranges and things like that. Okay, the most incredible feature about Venus, and who was the author that said that women are from Venus? Never, I didn't say that, did I? Okay, sorry about that. Okay. But the other thing about it, if you look at the mass, it's the one with the mass closest to that of Earth. 0.82 of Earth's mass. Okay? Diameter in kilometer, look how close. Earth is 12,756, Venus is 12,104. Closest in size. Okay? Earth radius 0.95 of Earth being 1. Density, it's the close to being the closest density to Earth. Actually, Mercury is the closest to being density to Earth, but then Venus is shortly there behind. Notice how the terrestrial planets with densities are all just about, really close to each other. When you get to the gas giants, very low density. Okay. Atmosphere, mostly CO2 with some other stuff. And of course, this thing about solar energy received in calories per centimeter squared per second, that's just because the closest one get more solar energy, the further out you get the less solar energy. That's not a surprising thing at all. Look at the data there. Okay. Now, this is a terrible slide, okay? Who can read that? I can't read it looking at my computer here. I can in the book. The table 15.2 in the book is your spacecraft missions to Venus. And if you look at that just glancing, most of them was USSR. When the Soviet Union had a space agency, they focused on Venus. That was the closest planet to us. Of course, if they focused on Venus, then we went to Mars. I mean, no, it's sort of like the French and the British. If the French believe one way, the British are going to believe something else. I mean, it's just about that way. Okay. But we did get lots of good information from many, many, many missions. Even if the primary goal wasn't to visit there, anything going out into space, why not send it by Venus? It's close, so let them take some pictures, take some measurements, or whatever. It says, how many times would a space probe on Venus' surface have gone around the sun if it had been there 30 Earth years? So that's just talking about how slow Venus is going, that kind of stuff. So they sort of make up questions, these examples. They're nothing all that useful to know. All right. Here is a picture. Let's see if this is in your book. It was in the previous edition. It's not in this edition, I don't think. Okay? I don't know why. It's a neat little picture. Okay, remember the surface of Venus is very hot. Okay? You won't see a river on Venus. It would all be evaporated if there was any, okay? It's very hot. This is a volcano, which I don't know if it's currently active or not, huge mountain on Venus, okay? These are lava flows, okay? Probably coming out of the thing, but goodness, the surface is so hot, that stuff doesn't harden very quickly. I mean, so that could have been around quite a while. As I said, you don't want to go there. No space trips to Venus anytime soon. Okay. When they say mostly flat but varied, that's varied. All right. Now notice what planet we're leaving out. Earth. Okay. In the table, Earth is mentioned. And let me just mention a few things about Earth. Of course, we're 1 astronomical unit from the sun, because that's how we define it. The distance, average distance from Earth to sun is 1 astronomical unit. We know our rotational period, close to 24 hours. We know our orbital period, close to 1 year. I mean, that's how we define it, 1 year, 365 days. The most interesting thing to me is we are the densest planet. Remember, Mercury was pretty close to us, and Venus not far away. Mars quite a bit less dense, and the gas giants nowhere close. We, Earth, are the densest planet. And that's sort of interesting because we have a fairly substantial atmosphere. We have a lot of water on our surface, which none of the other planets do, and yet we're still the densest planet. Not that that's that much compared to all the solid matter that we have, but it is. Okay. And thank goodness. And I guess here's the other thing. look on either side of us. I'm looking at the table on 381. What's the atmosphere of the planet closer to the sun? Venus. Carbon dioxide. Look at the atmosphere of the next planet out from us. Mars. Carbon dioxide. Okay? Where do we get being nitrogen and oxygen? Do any of the other planets have anything close to that? No. Now, I'm not absolutely certain about this, but I think I've read enough about it that the understanding I have, one reason that we have oxygen in our atmosphere, those little things right outside our window, green plants. Because green plants take carbon dioxide out of the atmosphere and put oxygen back in, because they are building themselves out of carbon. Okay? That's why all organic, all living things contain carbon, and the plants are taking our carbon dioxide. I'm beginning to suspect if it weren't for plants, we would be mostly a carbon dioxide atmosphere and could not support life as we know it. Thank you, plants. Okay? Nitrogen, I have no clue of where we get all the nitrogen. None of the other planets seem to have significant amounts of nitrogen, and I don't know why. Okay. Now, I do know that oxygen is a very active element. It combines with anything it can get in touch with, but because green plants are pulling out the oxygen out of carbon dioxide and putting it out as elemental oxygen, that's why we have it. We would not be here if they were not here. Okay? Period. Nowhere close. Okay. All right. So let's move on to Mars. Okay, now remember, Mercury, 0.4 astronomical units. Venus, 0.7, Earth, 1. Mars, 1.5. So, the distance from Sun to Earth, if you take half that, that's somewhere just outside Mercury's orbit, inside Venus's orbit. That plus this, halfway again, that's the orbital distance of Mars. How far Mars is from the Sun. So 0.4 between the Sun and Mercury, 0.3 between Mercury and Venus, 0.3 between Venus and Earth, 0.5 between Earth and Mars. We're getting further apart, okay? Planets are. Mars has geologically active regions and some not so active, inactive volcanoes, but in the past they were active. It has canyons. Wait a minute, what makes a canyon? What makes a Grand Canyon? Water. Okay? What could have made the canyons on Mars? Could it have been water? There's not measurable or significant water on the surface of Mars now, but maybe sometime in its past it could have had water. We know there's water under the surface in the form of ice near the poles. There's water on Mars, but that's the only other planet I know of that's significant amounts of water. Maybe some of the others. So it makes you wonder what made those canyons. Now, you also have terraced plateaus near the poles and flat regions pitted with craters. Now, what does that usually mean?
What do you mean? Which part?
That you have pitted with craters. And therefore, not much atmosphere to protect it. So this next statement, thin atmosphere, pitted with craters, they go hand in hand. But that thin atmosphere is mostly CO2, carbon dioxide. So, again, pitted with craters means that your atmosphere is pretty thin. Earth, for instance, we don't have very many measurable craters on the surface of Earth because we have a pretty decent atmosphere Most of the stuff that comes in gets burned up before it reaches here. Okay, strong evidence for liquid water in the past, as in those canyons, but none in the present. Some solid water, as in ice, underneath the poles, but no evidence for liquid water now. Any evidence there really was ever life there? Not really. Water would have to be there, and if there was water, there could have been, but we don't have any evidence of it. Now, I don't know the most recent thing, but you know, we currently have several rovers that are crawling around on the surface of Mars in different places, picking up data all over the place and sending the data back. I haven't read or heard of if they found anything, but they're looking for any kind of organic compounds there that could have come from life. As far as I know, they haven't found it. But I haven't been keeping up with it. Okay. Numerous space probes. Okay. This is supposed to be telling you a lot, but you'll notice on one side you have a gradual slope, on the other side it's pretty sheer. What we call that except possibly water eroding this? I don't know. That's why they do those studies. Now this is not some bizarre thing on the surface of Mars. Something landed there and took off there and packed it in. This is what mostly Mars looks like. It's called the red planet. Why?
Because it's not very hot.
Yeah.
Okay, no, none of the planets are hot enough to give off any light, so it's not giving off light. Yeah,
That's stars.
that's stars.
Why is it red?
Iron oxide, which is rust, which is oxygen combined with iron. Like I said, oxygen is going to combine with anything it can. So there probably is presence of oxygen there, but it's not in the atmosphere, except combined with carbon. And on the ground, combined with iron, okay? But usually rust happens more where there's been water present, right? So there probably also indicates that it's somewhat water has been there anyway, sometime in the past. All right. They didn't show the probes. They just said numerous space probes. If you turn to page 385, there are your missions to Mars. Okay? More to Venus, it's closer, but quite a few to Mars. Okay? And if you look there, you'll see the U.S. is leading USSR. Not by as much as USSR led in Venus, but you know, still we. Now you see another couple of unusual things there. What in the world is ESA? This was in 2003 and 4. ESA. European Space Agency. Europe got into the game. For a while before 2000, from 1950s and 60s to 2000, it was all USSR and USA. That's all. Beginning around 2000 or so, maybe a little before that, European Space Agency got involved with it. And then there's one more. 2014, who do you notice is there? India. So India has capability of sending out things.
India.
Oh, geez, I was wondering why Hubbard didn't have that.
What's that?
So I was wondering why Hubbard doesn't have that. That's because I have the 8th edition.
You got an older edition. Okay. All right. You don't need to know that for the thing, but okay. Now, interesting little example on page 385. If the noontime surface of Mars can reach as high as 20 degrees Celsius, does anyone know what 20 degrees Celsius is approximately? Say again? Is that cold, hot? Okay, 20 degrees Celsius, room temperature. We're really close to 20 degrees Celsius right now. 68 degrees Fahrenheit is 20 degrees Celsius. Okay? Is that warmer or colder than a typical room temperature of 72 degrees Fahrenheit? That's just a little bit cooler. And this is using stuff from before. I thought it was going to be more significant than that. It's not. Sorry. Mars' coldest temperatures are around negative 140 Celsius. Okay? What is that temperature in Fahrenheit? That's about negative 220 degrees Fahrenheit. I don't think any place on the surface of the Earth anywhere close to that. Antarctica, Arctic Circle, nowhere close. So there's not going to be very much liquid water there. All right. Now, there's a pretty interesting figure on page 384 showing relative sizes of planets, the 4 terrestrial planets. Mercury, very, very small. Venus, Earth, almost the same size. Earth has this moon, and notice that moon for Earth is almost as big as Mercury. Not quite, but close. Then we have Mars, which is bigger than Mercury, but still pretty small. It actually has 2 moons. It only shows 1. Those are tiny little BBs compared to our moon. I mean, ours is a good-sized moon. That's a pretty good descriptive picture. The scales, different distances apart, nowhere close. They just interposed them here. Okay. It looks like we have a fair amount of movement here. It's probably not a bad time for a little break, is it?
Good idea.
All right. All right. Okay. Before we leave Mars, I want to talk about a couple more things, but let's take a break. Try to keep it. All right. Before we leave Mars, there is, I think, a really interesting question. That's on page 386. It's a case study, Worth the Cost is the title. And I know there's a lot of discussion about that. Why are we spending so much money here when we could be spending it somewhere else? You know, that type of thing. It's a pretty good little blurb. I'd say it's worth a read. You can make up your own mind if you think it is worth the cost or not. Okay? But it's a pretty good question. Huh?
It's a lot of taxpayer money.
It is, but we do learn a lot too. An awful lot. In fact, if you think about it, I'm not absolutely certain of this, but I'm pretty sure it is. Any of you ever use Velcro? Okay. You know why Velcro was created? So they could get things to stay in place on a spaceship. Because when they're doing that, things would tend to fly around, you know. And Velcro enabled them to have a very lightweight way of sticking something, but you can pull it right off. It's not permanently stuck or something else. So I'm not absolutely certain, but I'm almost certain that's just one thing. And that's just one of many things that we've either improved on or gotten very much better at or developed from scratch because of space. But I'll let you read that and decide. All right, let's move on to Jupiter. Now, what's in between Mars and Jupiter?
Earth. Oh, Jupiter.
Venus. What's in between Mars and Jupiter?
Yeah. What's in between Mars and Jupiter? The asteroid belt, of course, okay? Now, let's get our perspective here. Sun's here. Okay, let's have Earth. Let that be the Earth right there. Okay, if this is the Sun, 4/10 of the distance between Sun and Earth is Mercury. 7/10 is Venus. So there's 4/10, 3/10, 3/10. 5/10 to get to Mars. 5 times to get to Jupiter. Whoa! Everything was measured as tenths here. 3 tenths, 4 tenths, 4 tenths, 3 tenths, 3 tenths, 5 tenths. And then you have from 1.5 to 5, that's 3.5 times to get way out to Jupiter. That's far enough, you would almost think there ought to be another planet in there. Okay? Now, many people hypothesized that there was enough stuff there that should have formed another planet, but because Jupiter was so stinking massive, it kept that stuff from aggregating and becoming a planet. So they think that maybe Jupiter's gravitational field kept the asteroid belt from being a ninth planet. Okay? 5 astronomical units from the sun. So here we had the sun, Mercury, Venus, Earth, Mars, Jupiter 5 times out there, from here to there, 5 times out to Jupiter. Way out there. The most massive planet by far. 318 times Earth's mass. In the fourth terrestrial planet, we're the most massive. Jupiter, 318 times as massive as we are. And what's it made up of? Mostly hydrogen and helium. The lightest gases we've got. So there's a lot of those gases there. Now, it does have an iron silicate core. Okay? We're going to learn in the next chapter, we have an iron core. Not so much silicate, but iron. Silicates are on our surface, but Jupiter has an iron silicate core. So that's where a lot of the mass is. In fact, here is a cutaway of what we think Jupiter is like. The iron silicate core here itself is 10 to 15 times what our mass is. So you can fit 10 to 15 Earths just inside the core of Jupiter. Okay? That's a lot. Okay? 10 to 15 times as massive as the entire Earth is just the core of Jupiter. And that's iron silicate. They don't specify whether it's solid, liquid, or what. More than likely liquid. But it could be solid. Who knows? I do not know that. Okay? The next level here is liquid metallic hydrogen. My word, what do we mean by that? Hydrogen most of the time is what? A gas. It's the lightest gas there is. The only way you can make it a liquid is by, cooling it really down close to absolute zero, very close to absolute zero, or putting it under an enormous amount of pressure.
Is this just theory?
Yeah,
That's
I
right.
didn't know what's in it. No, I never been.
Okay? Well, we set probes there. Okay?
So we have been there?
There's what?
Probes been there? Yeah.
Okay. No, the probes don't. Okay. Actually, the probes have penetrated and gone down. How deep they've gone, I don't know. But they're able to measure the spectroscopy of it to see what makes it up. And also densities and temperatures and other things like this. That's how they put together the data.
Oh,
Okay. Now, that liquid metallic hydrogen here must be under an awful lot of pressure. That's the only way I can do it. Because I can't believe the temperature is that cold. It is cold out here, but this has to be awfully hot in here. So that can't be all due to temperature. I think it's due to pressure. This is liquid hydrogen, which that could be cold. That could be because of the cold environment that it's in. And then the atmosphere is mostly hydrogen, helium, ammonia, clouds. And boy, do they have some clouds. Some massive disturbances in those clouds. Storms that have gone on for decades, if not centuries. Okay? Hydrogen, helium, and ammonia. And if I'm not mistaken, a fair amount of CH4. We just talked about it, methane. Okay, probably a little less than what the others are. Okay, that is one big planet, one massive planet, and I could easily see, being that close to the asteroid belt, yanking away some of the asteroids and make moons out of them. You know, if they were going around the sun, now they're going around Jupiter. But still, so much less than what the sun is. But it's by far the most massive planet. All right. Here is a picture of Jupiter and some of those storms. The belts, and why the belts have these colors, I do not know for sure. Temperature is one thing, density is one thing, maybe the materials in them, but this is called the Great Red Spot. It is a storm that has been going on as long as we've been looking at Jupiter.
He said storm, what do you mean? What coming out of those clouds? Not rain, is what?
Okay. But it's a disturbance. Whether there's actually anything coming out of them is swirling, tornadic type thing, whether there's rain coming out or not.
Just in that one spot?
What's that?
Just in that one spot?
Well, no, there's all over the place. This is the biggest one. And that's called the Great Red Spot. Near it is another place that's one of the coldest items on the planet, if I'm not mistaken, the planet Jupiter. It has a very, very vigorously active atmosphere, swirling. It's usually storms are caused by changes of pressure and changes of temperature, and that's why. Whether there's anything, if there was anything falling out of it, it could be ammonia coming out as ammonia showers or rainfalls or something. I guess it's liquid hydrogen is down here. It could be hydrogen and helium coming out. I don't know. But big storms, mostly just the turbulence is what we're talking about with the storms. Okay? There should have been a slide there. It's not showing up. Now, your book has, I think, some slightly better pictures of it. And this is from Hubble Space Telescope, and that's the Great Red Spot. In your book, the new edition, it doesn't look nearly as red. It looks like a great yellow spot, but typically that. And it says Jupiter has tens of moons. Okay, I'm thinking beyond the 40s. I'm guessing pretty close to 50s. Okay, and again, they don't give you an exact number because they're always discovering more. Okay. Okay. I don't see anything too new here, but here's what I was talking about: a dynamic atmosphere, meaning it's moving, it's changing, it's interacting. Yeah. Okay. Mostly hydrogen, helium, ammonia, I thought methane, and water. Okay? That water is probably in the form of ice. It's such a cold place, I can't imagine that's any liquid water to be ice. And the Great Red Spot is the most dynamic of the features on the atmosphere. It is an enormous storm that has been going on for a long time. Now, it seems like I read, I can't remember if it's this book or somewhere else, it seems to be decreasing in size slightly. So maybe that storm is finally, after decades of being there, maybe even centuries of being there, it's finally beginning to dissipate. It has a large, large system of varying satellites. Now, let me say this about these four gas giants. All four of them have rings. They're just not very major rings except the ones of Saturn. Saturn are just dominant rings. But all four of Jupiter, Neptune, and Uranus also have minor rings. Okay? Nothing is noticeable as Saturn. Okay? And none of these pictures show that, but they do. And this is the closest I've gotten them to read. The old edition didn't say it had tens of moons. It just had a lot of moons. Okay. Now, there up here is the great red spot, and this is that white spot here, and I think they said this is the coldest part of the surface of Jupiter that's discovered. You'll read it in the text. I'm not sure you have that same figure in the new edition. I haven't seen it yet. The great red spot soars. I mean, it's like huge, tall cumulus clouds there, or something, above the surrounding clouds, and is the coldest place on the planet. So the great red spot is not that white part, but the great red spot is the coldest place. Okay. Now, here are the 4 moons. Your picture in the new text, a little bit better picture, I think, than this one. But this shows them this way. The 4 Galilean moons. Why are they called the Galilean moons? Galileo, who improved on the first telescope. He didn't invent the first telescope, but he made major, major improvements on it. When he looked and saw Jupiter, he saw not just this thing that looked like it might be a star. He saw this actual body there with 4 other bodies rotating around it. And he said, wait a minute, this is what convinced him that Copernicus may have been right. He could see that Jupiter spun. He could see that great red spot moving, okay? Night after night, it had changed position. And he saw things going around Jupiter, these 4 moons, named the Galilean moons. Now, his telescope wasn't strong enough to see the others. He only saw the 4 big ones here. And these are from left to right, and in your book, it would be upper left, I think, 1, 2, 3, 4, okay? Upper left to right, lower left to right, okay? And they are Io, Europa, which is the smallest one, Ganymede, which is the largest one, and Callisto. Oh, I'm sorry. I got it out of order. Left to right, Io, Europa, Ganymede, and Callisto. I got it right. Okay. Io and Europa, the 2 small ones, are about the size of Earth's moon. Ganymede and Callisto are slightly larger than Mercury. These 2 moons of Jupiter are bigger than our first planet, Mercury. Okay, amazing the size there. And Jupiter has 4 of these things floating around it, plus tens of others that are going around, smaller. Okay, so our moon is about, how have we got a moon that's anywhere close to the size of the moon of Jupiter? And Jupiter is 318 times bigger than we are. Why would we have a moon that large? Actually, there's a theory about that. And I wonder if it's about the same time that something hit Venus and made it start spinning backwards. They think there was a major, major, major collision of something with the Earth way back early in our time, and actually knocked a chunk of the Earth off, and that made the moon. It was a very hot time, and we were still molten, so we reformed into a sphere. The moon reformed into a sphere, and a couple of reasons to suspect that. The moon, the same side of the moon always faces the Earth. You never, ever see the side of the moon. Ever. Except if you're in a spacecraft, they've seen it now. But we always see the same face of the moon. That would indicate maybe it did break away from us. And it's been going around just like that ever since. That may be why we have one of the biggest moons in the solar system, and we're one of the 4 smallest planets in the solar system, because it's actually part of us. Who knows? No one was there to measure it. Okay. Let's see if there's anything else. There will be something else coming up, and why it's not showing here. Let me just see if it's somewhere up. Oh, I know where it's not. We're going to catch it in a minute, and either today or next time. But they're showing it here in the section under Jupiter. In our text, it's going to be shown on the section under comets. Okay. Let's go back to the table and see if there's anything else we can notice on the table there. Jupiter. What's that?
I was reading the slide. It's 30 satellites.
Okay, yeah. Now that is Saturn. I changed from Jupiter to Saturn. But I was going back just to check if there's anything about Jupiter I need to say. I don't recognize anything. Okay. One thing about the rotation period. Remember, Mercury, very slow rotating. Venus, very slow rotating backwards. But then Earth and Mars, almost identical rotation periods, right at 24 hours. We're a little less, they're a little greater. But then when you get to the gas giants, they're really spinning quite fast. If you consider how big they are, 9 hours, 10 hours, 16 hours, and Uranus, minus 17 hours. It also spins backward, but not nearly as slow as Venus did, negative 243 days. Okay, whereas the orbital period, the further out you get, the longer it takes to go around. So that makes sense too. Okay, so I don't see anything too special. Now, density of the gas giants, actually Neptune is the most dense, followed by Jupiter, very close to Uranus, and Saturn's the least dense, but we'll get to that in a minute. So, the picture on page 389 is where a comet got too close to Jupiter and Jupiter sucked it in. But we'll talk about that a little bit later. Okay. All right. So let's move on to Saturn. Now, again, get these dimensions. Sun here, 4/10 of an astronomical unit, Mercury. Another 3/10 out, Venus. Another 3/10 out, Earth. 5/10 out, Mars. Another 3.5 out is Jupiter. Okay, so that's at 3.3. Okay, no 5. I'm sorry, 5, and then you get the Saturn, 9.5. From here on, they're almost doubling every time. Where these were fairly close together, now they're getting further away. The distance from Sun to Jupiter is almost the same distance as from Jupiter to Saturn. I mean, it's just unbelievable how far these things are apart. 9.5 astronomical units from the Sun. The rings of particles, and like I said, all of the gas giants have really small rings, minor rings, except Saturn, and it has these beautiful, beautiful rings. There is a sort of a picture in our text. I can't believe there's not one better. And the older one, in fact, I'll show it now. This is in there. The density, get this one. The density of Saturn is less than the density of water. If you had a big enough pool of water and put Saturn in it, it would float. None of the other planets will do that. Saturn is by far the least dense of all the planets. The surface is very similar to Jupiter's, just less dense. It has about 30 satellites. Like I said, I'm pretty sure Jupiter has in the neighborhood of 40 to 50. I think in excess of 50s. Now, Saturn has one of the biggest moons out there called Titan. Remember the Titan? Okay. It's the only moon in our solar system. The moon, this moon, has a substantial atmosphere. Mercury doesn't, okay? Mars doesn't have much of one. Titan, the biggest moon of Saturn, has a substantial atmosphere. Okay? Maybe even enough to support life. Way too cold. Way too cold. Okay. You've been here before, right? Oh, you're just getting here? First day. So you are Kedrick Deontay Williams? Yes. All right. Well, welcome to the class. Okay? All right. What do you go by the way? Kedrick. Okay. All right. Now, we've already finished chapter 14. We've done the lab for chapter 14. I can give you a copy of it. And we're scheduled to have a test on chapter 14 today. Let me just hazard a guess. You're probably not ready for it. All right. Okay. So you try to... Okay. Okay. All right. So here's the deal. I've recorded everything we've done. This is our third class, right? So the first class, I recorded about the syllabus, about research paper, how to do that, my locator card, and safety, and then we started chapter 14. That was that first Tuesday, last Tuesday. Last Thursday, we finished chapter 14, started the lab on chapter 14, actually started chapter 15 too, started the lab on 14, and then today we finished the lab on 14 and are proceeding in 15. In the last 30 minutes today we'll have the test on 14. If you want to, you can go on and go and try to. Okay, now here, say again? All right. Now, here's the deal. I record all the classes that are out there on YouTube. You can go look for PHS111, Physical Science 111, usually associated with my name, and they'll have different titles on them, and you can review everything we've done. Everything that's projected, everything I've said in sync. The only thing is you can't follow where I'm pointing things with my fan, because that doesn't get recorded. Okay, so I would say review that, and when you're ready to take the test, come and take it. If you could possibly do that within the next week, that would be great. If you need a little more time, that's fine too, because you're going to be having other labs. Let me go on and give you a copy of the lab. You will have to listen to the YouTube videos, and you can probably get just about all the questions off there. If you can't, there may be a few out there that you can get with classmates and do. Labs you can coordinate with. Okay. On the test, I know you probably won't do it today, but you can have with you a formula and equation sheet. Anything you want to write down on a piece of paper, it doesn't have to be formulas or equations. Anything you want to write down on a piece of paper, you can have with you during a test. So that can be done. Everybody has that option. Okay. Continuing now, we're in chapter 15. If you got the text, we're around page 390, and we're talking about Saturn. Okay. All right. Here's a picture of those rings of Saturn. And this was actually taken, I think this one was taken by the Cassini-Huygens, I believe, was the space probe that went to Saturn. It's European Space Agency and the U.S., I think, U.S. Space Agency, NASA, I think, worked together on that one. But it's mostly European. And they got some fantastic shots of some of these rings and other things. This is mostly particulate matter, as in dusty type matter. There could be chunks of rock in here, but there's also icy type stuff in here, okay? All solid type stuff, okay? Now, there is a picture in your text that's not on the slide set. Figure 1512 shows the rings and make up an enormous complex structure. From edge to edge, the ring system would not even fit in the distance between the Earth and the Moon. So Saturn's rings are reach further out than the distance between Earth and the Moon. So they are big, okay? And it names some of them, the D ring, the C ring, the B ring, the A ring, and then they name a bunch of other stuff, and here you'll see the Cassini-Saturn orbit insertion ring plane crossing, okay? This is when they took the pictures of all these things. And notice, though, the rings are in close. The moons of Saturn are quite a bit further out. Titan is way outside the farthest of the rings. Okay. Now, yes?
Do you know specifically why the rings are named after famous Greek heroes or gods and goddesses?
Why, I do not know, because certainly the Greeks were not the first to see them. No one saw those until the telescope, and the Greek culture was already long past. I am just guessing that because the Greeks were the earliest to view the atmosphere, I mean the stars and the skies, and to make up stories about them, I'm guessing more modern men just continued the process of thinking that, just like many of our constellations are Perseus and Hercules and who was the wing, Pegasus, and all those things showed up in the stories of the night skies, the constellations and stuff. So I'm guessing that modern man just continued naming them after some of the Greek characters. That's my guess. I don't know if that's true or not, but that would be my first response. Okay. I think if there's anything else related to, and again, I've told the others, this table that's on page 381 contains just scads of information. Saturn does have one of the gas giants that has the greatest inclination to the ecliptic. So it is a little out of kilter with the rest of them. Its density is the least by far. Yeah, nothing else is too extraordinary about it. We have sent quite a few probes there, Cassini-Huygens being one, and others. They always stop by Saturn if they can. It's such a pretty place to be. Now, poor Uranus and Neptune, they're so stinking far out there. We don't know a whole lot about them, but we have had some probes go by. But look how far they are. Remember, Sun, 4/10 of an astronomical unit, which that's the distance from Earth to Sun. So 4/10 of that way is Mercury. Another 3/10 out would be Venus. Another 3/10 out would be Earth. Then 5/10 further from Earth is Mars, and then 5 astronomical units, 5 times as far, more than 3 times from the Sun to Mars, you have Jupiter. And then it doubles again, almost to get to Saturn. Doubles again, because Saturn, remember, was 9.5. Uranus is 19. Doubled the distance from Sun to Saturn. It's another, that distance again from Saturn, from Saturn to Uranus. Goodness gracious, they're getting far apart. Really, really, really far apart. And then Neptune, not quite double that again. So far out there. These are the outermost gas planets, giant planets, gas giants. They very similar in internal structures to each other, which are both fairly similar to what Jupiter and Saturn are like internally. Not as big as either of those two, but still awfully, awfully big. Often considered sort of like sisters because they're so very similar to each other. Okay? This is a picture, I'm pretty sure, of Uranus. Now, what's not quite accurate about this picture, and you see it better in the one in your text, the photo image of Uranus taken from the Hubble Space Telescope, notice how Uranus's atmosphere weather bands and ring system is tipped on its side as compared to Saturn. Saturn is pretty much in the plane of its ecliptic with the Sun. Uranus is tilted the other way. So it's rotating like this. It's I think, the weirdest thing in the solar system. Venus turning backwards is pretty weird. The fact that Uranus' axis is not perpendicular to the ecliptic, it's almost parallel to the ecliptic. It's turning like this. I don't know what a day is like on Uranus, because the sun doesn't really set, it moves around like this, you know. It's bizarre, okay? Totally bizarre, okay? I was trying to see if there's any other things listed here. And that's why on page 381, the table there about Uranus, it says minus 17. That doesn't indicate is the axis is. So our axis is 23.5 degrees of a tilt. It's more like 90 degrees of a tilt. It's totally strange. Really, really strange. Okay, not exactly 90, but close to it. All right. This text does have a picture of Neptune that the previous did not. This is again from Hubble Space Telescope. Nearly the same size as Uranus, but is more than twice as far away from the Sun than Uranus. Well, not than Uranus is. Close to it, but not twice. Uranus is 19 astronomical units. Neptune is 30. Way, way out there. Okay? Now, if we had counted Pluto on average is even further than Neptune, but because of its highly elliptical orbit, sometimes it's inside Neptune's orbit, and sometimes it's way, way outside Neptune's orbit. Another reason it's not counted a planet anymore. Okay. And while both of these are smaller than Saturn and Jupiter, they're more than 4 times larger than the Earth. No comparison, really. Okay. Now let's get to the smaller bodies in the solar system. Smaller bodies, 3 general classifications. The first of these, the comets. I don't know why they list them first. I guess there's more of them. The asteroids, and then the meteorites. And I really hate they call it meteorites. They should be calling that meteoroids. Okay? Because does anyone know the difference between a meteoroid, a meteor, and a meteorite? We're going to get to it later. A meteoroid is anything floating out there in the atmosphere. Okay? a meteor is when it happens to intersect with the Earth's orbit, and then it heats up in the Earth's atmosphere and burns. Those are shooting stars. Okay? That becomes a meteor. It's a meteorite only if it lands on the surface of the Earth. If it doesn't all burn up and some of it makes its way to the surface, that's a meteorite. So this should be meteoroid, not right. Because there's a lot more out there than will ever intersect with the Earth or even land on the Earth. Now, what is this stuff? All of this? Leftover from the solar and planetary formation. The sun formed using most of the mass, like 700 times the mass of everything else in the solar system. The planets then formed with a bunch of the other mass that was left, and then the leftover mass out there, dust and particles and rocks and whatever, that's what these smaller bodies are. Now here's a statement that I was warning you about before. The combined mass of all these smaller bodies, the comets, the asteroids, and meteoroids, may be 2/3 of the total solar system mass. Impossible if the sun is 700 times more massive than everything else. So this means of everything except the sun. So don't think that includes the sun. The mass of the smaller bodies may be 2/3 of the total solar system mass other than the sun. The sun can't be 700 times more massive than everything else and be 1/3 of that. It just doesn't make sense. Now, this was the picture I was referring to back in Jupiter. There was a comet, once upon a time, named Schumacher-Levy. Probably named after the two people who first saw it. You know, they may have seen it independently and reported it. Schumacher-Levy. Poor Schumacher-Levy got too close to Jupiter on its way in toward the sun. Jupiter pulled it apart and it crashed on the surface of Jupiter. Remember, Jupiter doesn't have a solid surface, it's a gaseous surface, but it hit that atmosphere, and this was July of 1994. Now, one of the interesting things about this to me is no one saw it actually happen, but who first witnessed the result of this? Some professional astronomer in the U.S., in USSR. Say again?
He was on the moon.
Oh, is that? Okay. Who it was an amateur night watcher. Just someone who enjoyed looking through his telescope out in the thing, and he saw these pattern like this, or something like this, when he was looking at Jupiter and said, what is that? So he wrote, this is 1994, so I don't think they had internet back then, but somehow he got in touch with the NASA or the IAU or something like that, and he asked, what is this? They said, what's what? And they went out and looked themselves, and sure enough, they found out the comet had crashed in Jupiter. So was it something done by a professional? He was an amateur just out there enjoying his telescope. Broke into at least 9 big fragments, and those are the dots you see across the surface of Jupiter. Okay. Now,
It's 3:45.
it is 3:45. It's time for a new roll. Okay. And by the way, 100% attendance today, folks. Way to go. Okay, I think Hunter's still here. Okay.
You ever heard of the Dugon tribe?
What's that?
The Dugon tribe.
One-
The Dugon tribe
No, I haven't.
in West Africa.
Uh-uh.
They're on record for discovering a serious aid bag. I can't think of how long ago it was. But that was before telescopes.
Oh, really?
Yeah. You should
Wow.
check it out.
Ah, interesting.
Yeah. They knew about Sirius A and Cyrus A and Cyrus B.
Huh.
No, so
Serious. Yeah.
yeah, Sirius. It's in.
Okay. I'm still learning names and faces. LaShondra here, right? Yeah. and Rachel, and Trey. Okay. Yeah, Trey, he's right. Okay. All right. I was thinking this earlier, and it just struck me as a little funny. I think I have more A's in this class than any class I've ever had, at least proportionally. I'm not talking about grades. 4 people whose last name starts with A. Okay, I don't think I've had that. And this is just a sort of a little bit more than average size class. Okay, Jarrell is there. Whoops. Cece is there. Anthony is... Have we lost Anthony? I guess we did. He was sitting there, wasn't he? So I guess he's not permanently gone. His stuff's still here. Sean is back there. Fred is there. Chelsea is here. Sam is there. Nick is here. Melva. Willie. Lisa. I'm trying to find Tiara. I know she's here somewhere. There you go. Okay. All right. Anil, did we lose him? He was? No, there. Yeah, I'm sorry. You're over there. I have another Anil in my other class. He sits over here. So, in the other class. Ashlyn's still here. Kendrick is still here. And Anthony came back. Perfect attendance again. Way to go. All right. So let's move on with, okay. It's 3:45. At 5:15, please get me to stop so I can give you your test. Okay. So let's look at the comments. What's that? I think so, yeah. It's a pretty short test.
How many questions?
It's, this is a little shorter than normal, but it's 15 questions, multiple choice. All right. Okay. Comments are classified basically by where they come from. 2 sources of them. One is called the Oort cloud. Now that has to be named after somebody. I don't think anyone would make up a name like that. But they never mentioned who in the world Oort was. So that could be a potential paper topic. Who in the world is Oort? How did he come up with finding these things? You know, that type of thing. The Oort cloud. Now these are the long period comets. The ones that come greater than every 200 years. They make their circle, not circle, ellipse. They come close to the sun and then head back way out there. 200 years later, greater than 200 years later, they'll come back in again. These are from 30 astronomical units. By the way, that was about Neptune's range, to a light year away. Way, way out there. Okay. Now, I've heard it pronounced several ways. I think it's pronounced Kuiper belt. So I've heard some people call it Kuiper belt, but I think the U.S. pronunciation is Kuiper. Probably whoever it's named after may have called himself Kuiper. I don't know. I actually heard one lady at Birmingham Southern call it the Jupiter belt, and I thought, I've been misspelling all this time. And then I looked and got out to the vehicle and looked in. I was in the truck then. Looked in my book. No, I was pronouncing it right. She misspelled it. Okay, this is the origin of the short period comets. Short period meaning less than 200 years in a cycle. Now, the Oort cloud is all around the sun. Okay, all around there. It looks like a big sphere around the sun. Whereas the Kuiper belt is a disc-shaped region anywhere from 30 to 100 AUs from the sun. So you see there's a fair amount of overlap. But the Oort cloud is a huge cloud this way. The Kuiper belt is basically in the same disk of the planets. Okay? They're just further out. From Neptune on out. And one of those figures in your book kind of indicated that. I thought I saw it, but I'm not seeing it now. Oh, here it is. It may be the one on page 393, but I thought I saw something else. I thought did a pretty good job of illustrating, but I don't see it now. Sorry about that. Ah, here we go. Yeah, on page 380, when they showed, these still aren't representative, but when you see the sun there and then Mercury and the others, that's closer to relative sizes. The distances are closer, but they're not expanding as fast as they really are. Okay, but then outside Neptune, you see the Kuiper belt objects. Those are your comets. The one on figure 15.2 on page 380. Okay, there is another. The Oort cloud, this is 1515, and the Kuiper belt on page 393. There's another one. I can't remember if they show up on here or not. Okay, so what in the world causes these things to happen? Well, for a long time, they thought the comets were on regular cycles, sort of like Old Faithful or something. For instance, one of the most famous is Halley's Comet, because it was very, very, very visible back around the turn of the 19th to 20th century. And they thought it came about every 70 years, and I think it did. However, when it showed up during my lifetime, which was I think when that was, late 80s, 1980s or early 1990s, Halley's Comet was back where it should have been visible. It was still so far away and so small, you had to really strain to see it. Whereas when it came the previous time, it was bright enough, everybody was scared. The world's going to end, type thing. It still wasn't super bright.
How do they know that's the same kind?
What's that?
How do you know it's the same one?
How do you know it's the same one?
Yeah.
Oh, they asked. No, I'm just kidding. No, they were able to track it pretty much, and again, modeled it, and they predicted it, and sure enough, it came pretty close to the time they said. Okay, they studied these, the dynamics of what makes it go around the sun. That's all physics, and they can pretty much model it pretty much from that. But you see some of these out here that 200 years and greater, and some of these others, they aren't that regular. Of course, I mean, no one sees two of them in a lifetime because they're so far out there, and history hasn't been recording long enough to get more than one or two cycles of them, and they're just not that regular. What happens? Some sort of a gravitational nudge deflects the object to the sun, and when it does, it comes, gets closer to the sun, and then flies back out again. Okay? Some may get really close, some not so close, but they go very elliptical orbits. Okay. Now they also change speeds big time too. The closer they are to the sun, the faster they're moving. The farther they are to the sun, they're really creeping along there. Okay. So these gravitational nudges deflect them and make them come in, and then they make their cycle and then go back out again. Let's see if we get, here's a decent picture of it. I think the one you have in your book is a little bit better than this one, but it's the same general concept. Okay? What it doesn't show is the Kuiper belt. This is mostly showing the Oort cloud. Okay? And my best guess of looking at this and looking at theirs, if our solar system is in here, and most of the planets go pretty close to being, this is Uranus and Neptune. You see they're almost in the same plane. There's Pluto, like that. Okay? Now, from Neptune on out, okay, you have the Kuiper belt, and that's sort of this part in here. But the Oort cloud is all of this. Okay? So the Kuiper belt is pretty much in the same plane as the rest of the solar system, the planets and stuff, but the Oort cloud is just all around, scattered throughout there. No wonder they say that the total mass of all this is 2/3 of the mass of the entire solar system except for the sun. The sun is obviously the greatest mass. You see, even on a scale like this, the sun looks small because it's there. But this is just dust particles, just incredibly, but held by the gravitational force of the sun. Okay? So all that stuff added together would be more than the mass of the planets and the moons. Okay. Now, how are comets structured? We talked about where they came from, the Oort cloud or the Kuiper belt. How are they structured? Well, they're small solid objects, and one description has been a dirty snowball. Okay. Now, what does that mean? Frozen water, but also frozen CO2. Does anyone know what we call frozen CO2? Huh? You almost had it.
Dry ice?
Dry ice, exactly. If you've been to rock concerts or things like this and they have that smoky singing stuff there, really that's not dry ice itself. They have dry ice that is so cold that it solidifies the water, makes clouds, and that's what you have is condensed water like that, but it's from dry ice. When I was doing some testing for it was actually something to do with a lawsuit, I never knew which side it was on, and we were having to send samples from out near Anniston back to wherever they were being sent to. We stored the samples in dry ice to try to keep them from, the variations in airplane travel and stuff like this, to try to keep them fairly constant. So frozen water, frozen carbon dioxide, probably frozen ammonia, and probably frozen methane, okay? That's the icy part. That's the snowball part. And then attached to that, or part of that, is dusty and rocky bits. That's the dirty part, okay? So you got solid particles of rocks and dust and stuff like this embedded in frozen water, carbon dioxide, ammonia, and methane. So that's the solid part. That makes up most of what they call the comet head. Solid nucleus, but then you have a coma of gas. Okay? Let's see if we can get a figure here. The one in the book is going the different direction from this one, but it's the same thing. Here is this head. Okay, the solid nucleus. The gases are going like this. Okay? Does anyone know where the sun is here? It's in front of it, always. Does anyone know what direction this is heading? Okay, you can't tell. Even if it's going away from the sun, it still points like that. So it would be backing up, going away from the sun, going around the sun. This turns around. Always the head is toward the sun, and the coma of gases is away from the sun. Whether it's coming in or going out, it's always like that. Seems bizarre, but that's how it is. Okay? So that's the comet head, solid nucleus, dirty snowball type thing, with a coma of gas around it. Two types of tails. Ionized gases. What do we mean by an ion? Okay, it's what makes up stars. What it is a gas that energy has been added to it, like cosmic energy or something like that, and has knocked off electrons or gained electrons. So it's now neutral, not electrically neutral. It's either positive charge or negative charge. That's what it ions. And these are ionized gases that are out there, or they're dust. Now, if they're ionized gases, they could be producing their own light. If they're dust, they're reflecting the light of the sun. Okay? And it's hard to tell which. Both types of tails are there. The tail always points away from the sun. If it's coming in, then the tail certainly is pointing away from the sun. If it's going around the sun, the tail always points around. If it's going out, the tail still points. The head's here, and the tail is still pointing away from the sun as it goes out. The tail always points away from the sun. So therefore, the head is always pointing toward the sun, no matter which way it's heading. Okay, so those were our comments. Main classification of them. Now, I wish I had said a little bit more about one thing. It's the mineral composition. No, I guess they're going to talk about that in meteors. Okay, don't worry about that in the comments. Okay, now we get the asteroids. The asteroids are located where? Between Mars and Jupiter. It's a belt in there. Now they go up to about 1,000 kilometers in diameter, I think that's talking about. Very composition. The innermost ones of those are more on the stony side, sort of like the terrestrial planets that they're closest to. The outer belt are dark with carbon. Okay? Others in between have varying amounts of iron and nickel. Okay? So there's a varied composition. And this is just a general classification. We think there were leftovers from that original solar nebula when the sun was blowing up and spewing stuff out and bringing stuff in, it's leftover from that. They feel like, many people feel like, that would have clumped, they have a better word for that, but clumped to form another planet, but Jupiter was just too strong of a gravitational field to allow that to happen. So it stayed a belt of trash, okay, of varying materials. That's the asteroids. Okay? Now, again, reminding you, if the sun is here, Mars is here, that's 1.5 astronomical units, so the Earth would be something about here, 2/3 of the way out. Okay? If you gauge the difference between Mars and Jupiter, about 4/10 of that distance, between the Sun and Jupiter, about 4/10 of that distance is the inner part of the belt, 6/10 of that distance is the outer part. So it's a fairly narrow belt, comparatively. Okay? You would have thought there should be a planet there. Okay? And maybe there should have been. Jupiter kept it happening. Okay? Now we get to meteors and meteorites. Okay? Now, again, they should have said earlier meteoroids. Those are remnants, stuff left over after that sun's formation period, and it blew stuff out and sucked things in and stuff like this. The meteoroids are the other chunks of stuff that's in closer than the comets, but not in the belt of the asteroids. These are the meteoroids. They're all over within our solar system. Not that many of them, but there are some. Okay? Now, some of those meteoroids, remember now, what was a comet made up of?
Snowball.
Dirty snowball, exactly.
Come on now.
Dirty snowball. Now the snowball was made up of ice, solid carbon dioxide, solid methane, solid ammonia. Okay? Guess what? As they get closer to the sun, some of that starts melting. Okay? And as it starts melting, then some of the dirty stuff, the chunks of rock and stuff, come out of it. And they're just left hanging around. That's what makes the meteoroids. Remains of the comets or asteroids that may have been in the asteroid belt, but because of some gravitational nudge or something, they got forced out. Maybe Mars sort of pulled them but didn't yank them close enough or whatever, and they start filling in the gap. These make up the meteoroids. Now, it becomes a meteor only when it encounters the Earth's atmosphere. If it crashes into the moon, it does. It doesn't become a meteor. It's a meteoroid that crashes into the moon. If it crashes into Jupiter, into Mars, those are meteoroids that happen to hit. But if that meteoroid enters the Earth's atmosphere, then it starts heating up. That's what makes it a meteor. Now, we have what they call meteor showers. These are when the Earth is passing through where a comet came through, left its trash behind, and then we get more of these meteors then. Okay? What's a meteorite? It's a meteor that actually didn't burn up all the way and survives to strike the Earth's surface. They have found several types. Iron meteorites, stony meteorites, which would have in them the silicates more. Now, the stony meteorites are chondrites and achondrites. Okay? And then the third kind is stony and iron. Now, the chondrites and achondrites. Okay? I'll read you what they say here, and then I'll give you my interpretation of it. Okay? The stony meteorites, right there, are further subdivided into two groups according to their structure, the chondrites and the achondrites. Okay? Chondrites have a structure of small spherical bodies, lumps, that'll be silicate minerals or glass, called chondrules. So that's what makes them chondrites. Held together by a fine-grained cement, sort of like the mortar that held together the blocks here. Okay, something like that. It's not necessarily that. The achondrites do not have the chondrules or the spherical things. They're just irregularly shaped. Okay. Now, but they do have homogeneous texture, more like volcanic rocks, such as basalts that are cooled from molten rock. So that sort of gives you an idea, maybe. Have any of you worked anywhere around steel mills? Okay. When you have that really hot gases and stuff like this, and stuff when they're melting the iron ore and stuff like this, there are some solids that actually evaporate and go up into the stacks, and as they cool, they come out as little spherical bodies. Don't they call it, is that called slag or? Slag. Okay? That to me is what the chondrules are. Little spherical bodies that must have been at some time when things were very, very hot, evaporated, and then when they cooled, they formed these spherical bodies. Those are the chondrites. They're chondrules, but that makes a chondrite stony meteorites. Whereas the achondrites, they were chunks that didn't completely melt and then reform as spheres, but they're irregularly shaped, that they look more like volcanic rock that made sort of glassy, shiny surfaces. Okay? Didn't make the perfect spheres. To me, that's the difference there. Slag and just leftover trash. Okay. Now, the iron meteorites are about half as abundant as the stony meteorites. So stony is the biggest part. iron next, and then in general there's some that are a mix between the two. Okay. There is a statement here. A meteorite is not, as commonly believed, a ball of fire that burns up in the landscape where it lands. The iron or rock has been in a deep freeze in space for some time, travels rapidly through the Earth's atmosphere. The outer layers become hot enough to melt, but there's sufficient time for that heat to be conducted on the inside. Insufficient time. So the newly fallen iron meteorite will be hot, since the metals are good heat conductors, but will not be hot enough to start a fire. So you usually don't have fires being hit by meteorites, started by meteorites. Blah, blah, blah. Okay. Here are some of those meteor showers, and then you'll see them. Quadrant head, there must be some constellation called quadrant or something like that. On January the 3rd, not during this term, shortly after this term over, first of the year, about one meteor every 2 minutes. Okay, the hourly rate is 30 per hour. It would be one every 2 minutes. You should, if it's a clear night, be able to get a pretty good show out of that. Aquaid, that would be in Aquarius. I don't know these constellations. May 4th, that's only 5 an hour. That's one every 12 minutes. I think I'm going to get pretty bored and not really hang around for that. Perseid, wherever Perseus is, August 12th. We just had that. 40. That's about one every minute and a half. Okay? No, one every 40 seconds or something like that. Okay? Orionid, I know where Orion is. That's one of the easiest constellations for me to pick out. October 22nd, we'll have one of these this term. But it's still only one meteor about every 4 minutes. I don't know if I'll stay awake for that either. Okay. Taurids, in Taurus the bull, will hit it once November 1st and again November 16th on its way in and on its way out. I mean, the comet has already been there, but we go through its tail twice. Once on the tail that it left when it came in and the tail it left when it got out. But again, only one every 12 minutes. I'm probably not going to keep attention span that long. Leo the lion on November 17th, the very next night, 5 minutes, 5 per hour, one every 12 minutes. But December 12th, right at the end of the term, in Gemini, which I'm not sure I can pick out Gemini either, but there should be a one just about every minute. So if it's a clear night on December 12th, now you have to pick the right time too, and you'll have to read in the paper to see when that is. But sometime around December 12th, you should be able to see a pretty good show. A meteor about once a minute. Okay, not quite. Once every minute, 5 seconds or something like that. All right. So those are meteors. Leftover pieces out of comets, leftover pieces, asteroids that fell out of the asteroid belt, or just junk that's out there. All right, here's a picture of some of those. And by the way, the picture in the text, figure 1519, shows sort of some of this stuff, but they have a picture of the night sky. Now, this is a time-lapse image of a meteor shower. Not all those are happening at the same time. Believe me. This is probably you kept the aperture open for probably hours, and you saw these various streaks going across. Notice it doesn't seem to be any pattern in them. They just are showing up, flashing, and disappearing. All right. This is a picture of, I think the one, I don't have the book that has this, I think the one on the left, and it seems backward to me. The first one here I think is a stony meteorite, which to me looks like an iron meteorite should look. It says smooth black surface, yeah, was melted by compression in the atmosphere. So this is one that made its way to the Earth. The second of these is an iron meteorite. The one in the book is more realistic, I think, that has been polished and etched with acid. So basically, this is closest to the surface of the actual meteorite. The rest of it is the polishing and acid etching. It made it look so white. You'd expect iron to be dark, not white like this, but that's because it's been treated really, really heavily with acids and other things like this so they can do it. So the one in our book gives a lot better picture than that. Okay, in the new book. Okay. The pattern indicates the original material cooled from molten material over millions of years. It wasn't a rapid cooling, it was a very slow cooling. Now, I don't see how they get that out of that, but that's what they said it shows. Again, they have their ways. Okay. Now we enter 15.3. Okay. Okay. And that's the origin of the solar system. I've been hinting at this all the way along. Okay? Let's go back to what we did in the last chapter. How do planets begin? They began as a protoplanet. Before that, they were a nebula. But every nebula is not going to become a planet. If, however, it makes it to a protoplanet, that is what's going to make it into a planet. So this is the protoplanet nebular model. First, stage A. The formation of the heavy elements in many stars and supernovas, they came about when these massive stars went through repeated fusions. The first fusion is hydrogen to helium. The second fusion is helium to carbon. The fusions after that make carbon to iron. And that's about as far as you go with normal fusions. But then when you had a collapse from that and then a blowout, then you form the heavier elements beyond iron. And that happened in the huge stars and the supernovas when they collapse. Okay? So that's where you get this material. So that's where the material came from for our solar system, from all that. Now, you get concentration in one region of space as dust, gas, and chemical compounds. That's the leftover stuff from this. You get a concentration of it. Something happens, we don't know what, that starts the gravitational collapse. Some sort of, what do they call it? Sort of like a gravitational nudge, a wave of some nature that compresses things together. Once they compress and stick together, now they start pulling others in. That's called gravitational collapse. Okay, so this is stage A. Okay? Now, you have the gravitational collapse, things are heating up. When you get to the protoplanet stage, you just about are already past the place where you start having fusion. The hydrogen starts fusing to helium. Up until then, things have been collapsing, getting hotter and hotter and hotter. When they reach that critical temperature and get hot enough, now you have fusion happening and it's blowing things out. And it's not a very pretty organized thing. And it blows out here, but also in this disc here. Now, there has to be a reason for that. And I can't tell you exactly what it is. It has to do with angular momentum and other things like this, that you get this general shape of things. So this is stage A. Formation of the heavy elements from earlier stars and supernovas, concentration in one region, dust, gas, chemical compounds pulling together, getting hot enough to be a protoplanet. So fusion is just beginning to happen. It's a mess. So you see stuff is scattered throughout this. Okay? The center mess is going to focus in and become the star. The residual mess out here, that can form the planets, and then the mess that's left over after that, that's going to form all that other debris that's there. Okay, so here's stage B. Formation of a large rotating nebula. Okay, that's the end of that part. Gravitational contraction, the spin rate actually increases. So this is the sun contracting, speeding up, and it seems like to me that we tend to throw things out, but that actually coalesces them. Here's how to think about it. Have you ever watched the figure skaters in the Winter Olympics? And when those guys or gals start spinning, and the arms go out like this, they spin relatively slowly, but when they pull them in, they're going to drill a hole in the ice, it looks like. They go so fast. Same type thing here. Again, it has to do with angular momentum type stuff. Okay? So the gravitational contraction, and as it contracts, they actually spin faster. Okay? Most of the mass concentrates in the central protostar, not quite a star yet, but a protostar. This has all been gravitational collapse here, and then when it continues collapsing, you get the protostar here, you still have masses of gases floating around out here. The remaining material forms of what we call the accretion disk. The main part of that is the planetary axes, and you have the asteroid belt in that planetary axis. You have the Kuiper belt that basically is an extension beyond that, but that's in the accretion disk. You have other stuff out here, that's the Oort cloud. Okay, we talked about that. The material in the accretion disk begins to clump. Okay, they like that word clump. It doesn't sound very scientific, but it does. So Mercury clumped, Venus clumped, Earth clumped, Mars clumped. The next band tried to clump, but it couldn't because Jupiter was so strong it prevented it from clumping, gravitational field, and all of them clumped beyond that. Okay? This shows the inner four, basically. So that's the C part. So this is the beginning of the clumping stage. Stage C. The protostar finally becomes the sun. So you get that dynamical equilibrium there between the gravitational collapse and the fusion expansion. It becomes a star. You have solar ignition flare-up may have blown away the hydrogen and helium from the inner planets. Guess what? The closest planet has no atmosphere left at all. Venus collected some atmosphere, in fact, quite a bit. Why it kept any, I don't know, but it's a really thick, dense, heavy atmosphere, mostly carbon dioxide, but other kind of gruesome stuff. We got a really pure and nice atmosphere. Mars, not very much at all. But there's not much hydrogen and helium in here. Where did it get blown to? Out to the gas giants. That's the lightest stuff that got blown the furthest away. So that's why the gas giants are gas giants. Their inner cores are more like what these are, but you have all the hydrogen and helium around it. So blew the hydrogen and helium away from the inner planets to the gas giants. The protoplanets heated, separating the heavy and light minerals, most of the heavier going to the center, the light being on the fringes, you might say. And if you look at our planet, we'll talk about these later, you have the lighter materials, the granites and things like this, the silicates on the surface, and the heavier stuff like iron inside the surface, inside the planet. Happens over the long. Okay? And then the larger bodies cooled slower, with heavy materials settling over longer times in the central core, as I was saying before. So who knows what's in our core? We may have, well, tons of iron in there. We scour around and mine all the iron we can get that's on the surface. If you could drill into the core, you can get all the iron you would ever need. You could probably find also more uranium and plutonium and all that heavy type stuff in there. but who can do it? Okay. All right. That's your final stage. That's what made us a solar system. It's just showing the inner four planets, the terrestrial planets. Then you have the asteroid belt. Should have been a planet, but didn't. And then you. Sorry, have the gas giants out beyond that. So here are some ideas about that solar system in this model. I'm sorry.
You gotta go see about that Thursday, man. Go.
What's that?
You gotta go see about that car.
Okay, I think I will.
Okay.
I'm not exactly sure why they're bringing up these models at this point. Okay, this is more historic than it is fitting in here, but it's how we proceeded to get this. Early on, we thought the Earth was the center of everything, as most kids believe now too, don't they? Aren't you the center of the universe? Everything's supposed to revolve around you? Unfortunately, a lot of adults think that too. Okay, all right. But the attempt of the early astronomers and philosophers to explain the observed motions of the sun, moon, and stars. Everything seemed to go around the Earth, didn't it? So, I mean, they weren't being egocentric. They were just trying to explain what they were seeing. What they didn't know is we were spinning, and it made it look like things were going around. They were actually fixed. We weren't. Okay. But that was the early attempt. That the trying to describe how the sun moved, the earth, moon moved, the stars seemed to move, everything seemed to move. I don't know how I explained the North Star never moved, but anyway. This placed the Earth at the center of the orbits of all the planets, but the planets were a big problem because they didn't follow regular patterns. They sometimes went this way, sometimes back that way again. Exceptions of this model were explained by the Ptolemaic system. Ptolemy, I think that's how you pronounce his name, pretty sure he was Egyptian. I was thinking he was even like a pharaoh or something, but it may have been just a really bright scientist. You could call it a scientist back then. And he came up with all these ways to explain why the planets did this and the other things did it. But it was really complicated, and the inconsistencies in the system kept growing. He would predict things well for maybe 10 or 15 or 100 years or so, but then after that they fell out of sync again, so that wasn't working. They grew in number and became more complicated to explain. And here's the sad part, folks. The church, rather than leading society, was following society. And they were buying into all this stuff, and then were saying it was doctrine. So that the Earth has to be the center of the universe, you know. It really wasn't. I mean, there's not that much in the scripture that suggests this, but they made it seem like it was that. So when anyone came up with a better idea, no, you can't think that because that's not how it was. Okay? Well, the heliocentric model, when we finally said, look, things just aren't working this way. Ptolemy's corrections not working anymore, okay? Now the idea of the Earth going around the sun was developed by Copernicus. Now, Copernicus had something really positive in his favor. He was from Poland, a long way from Rome, okay? The seat of the Roman Catholic Church. And he was so far away they couldn't really prosecute him or persecute him very strongly. They didn't like him at all because he came up with this idea. But his suggestion of this started making all these inconsistencies in the geocentric models explained really simply. If you just had everything going around the sun, not around the Earth. Later, a guy, and by the way, all these people are good paper topics. Copernicus, Ptolemy, Kepler, or Kepler's laws, models. Any of these things are good paper topics. Kepler's laws would then further explain the heliocentric model. As Johannes Kepler can't remember if he was German or Dutch or Danish, I can't remember what, but he came up with, I mean, basically just analytically, there's another word for it that I can't think of, it's escaping me right now, that experimentally he just showed this model would work, but he couldn't explain why it worked. So he turned to this little guy, what was his name? Isaac Newton. He said, can you explain why this worked? And Newton came up with, well, he had to develop a whole map to do it, calculus, and explained all these motions really nicely, okay, with the use of calculus. And that's where his 3 laws of motion and those kind of things came from, helping Kepler explain why it worked, not just that it worked, but why it worked. And this then would lead further indication of the heliocentric model. Now, who was the guy that came along before Newton? There's 4 moons of Jupiter? Galileo. Okay, Galileo, his misfortune, when he got this telescope, improved on it, and looked out there and saw that the sun turned, Jupiter turned, the moon turned very slowly, the moon went around Earth, these other moons went around Jupiter. Why can't we be moving around the sun? Makes sense. If those others are spinning, we could be spinning. That could account for the apparent motion of the sun and the stars. That's why the North Star stays still and all the others moved around it. Hey, this is beginning to make sense. What was his disadvantage? He was from Pisa, Italy, which was really close to Rome. They said, if he hadn't been such a famous scientist, he probably would have been executed. But since he was such a famous scientist, they just put him under a house arrest and basically forced him to recant his support of Copernicus' model, the heliocentric model. And he said, no, I don't believe it, I was wrong, blah, blah, blah. And then he wrote to himself, and to be open after his death, I had to say that, so I really believe, and he continued writing, even under house arrest. But this is why the planet remained the planet. Here is the apparent motion of Mars, and you can't explain this with a geocentric model, okay? If we're here going around the sun, now this isn't what they believe, and there's Mars going around the sun. When we're here, Mars was there, and Mars was right there in the sky. Yeah, that's okay. When we were here, Mars was there, it looked like it was here. Hey, it's going on pretty regularly. When we were here, Mars was there. There's where it was. When we were here, Mars was there. Ooh, it sped up a little bit. Why did it do that? But then we were here, Mars was there. It backed up on itself. No, you're not supposed to do that, And then when we were here and Mars was there, it even went further back, and then it started going back and got regular again. So they called Mars and the other things that acted like this, like Mercury, if they saw it, Venus, Jupiter, they all followed these weird patterns. The stars were just like they were supposed to. These things didn't. So they called them the wanderers. That's what the word planet came from. The word wander. Because sometimes it went the right direction, sometimes it went the wrong direction, then it went back right again. Okay? They just wandered around. They were called planets. Not because, later the heliocentric model explained everything. Okay. All right. Looking in your text, if you have your text here, there is a neat little picture, but it's so small, and I'm not sure it explains it any better, the accretion model and that kind of stuff. That's on page 397. This is new in this edition of the book, as is figure 1519. Ideas about the solar system, that's what we just did. The apparent motion of Mars was just all over the place, whereas the stars were following regular patterns. Mars didn't, and some of the other planets didn't. These slightly different pictures from this one here, but they say the same thing. Copernicus, his system. Now, Kepler's 3 laws of motion, they do more in the book. They don't do anything in the slides. Okay? And as you read the book, here are basically, this won't be all 3 of his motions, mostly it. This basically describes the first thing. No planet follows a circular path. Some of them are really close, but all of them are elliptical paths. The sun is at one focus of the ellipse. There's nothing at the other focus, but we go around like this. Now, this is exaggerated. I don't know of a single planet that is that big of a change, that elliptical. Most of the time, these 2 foci are closer together, so those that are nearly circular orbit, they're really close together, okay? And Earth is not bad, but it is somewhat off. So that's the first law. All the planets follow elliptical orbits. The second law, this is what I was talking about before. When something is close to the sun, it's going faster. When it's further from the sun, it's going more slowly. But here's how Kepler did it. How he came up with this, just analytically, beyond me. But the closest point is called the perihelion. That's closest to the sun, helium, the sun. Aphelion is farthest from the sun, and that's when you're going the slowest. But the triangle, or sort of the sector that's mapped out by that, the areas are the same, with the same time limit. So if it's going faster here, it's going to be a thicker one, but it's closer this way. When they're further away, you've got more area this way, but less that way. And this is exaggerated again, big time. That's his second law. His third law related the period of the motion to the distance it was from the sun. And it's a weird combination. It's the ratio of the square of the periods is equal to the ratio of the cubes of the distances. Okay? Rather bizarre, but it works. And then this is sort of a byproduct of that. This is basically, I've mentioned it several times before. If you were to plot these on log scales, here's the period, there's the distance. And they did it in astronomical units, but you could have done it anyway. But you do it in a log scale. Look at where the planets fall. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Now, if you did this with Pluto in it, it doesn't fit. But with these 8, it does. That's probably the biggest reason we say Pluto's a dwarf planet, not a planet. And look at what looks like should be in here. Between Mars and Jupiter, a big gap there, like there should be another planet there. They would be nicely, evenly spaced if there were. That's the asteroid belt. Old Jupiter kept that from happening. Okay. So that basically winds up chapter 15. In your text, people behind the science, Gerard, Peter, and then they don't give a good explanation of how to pronounce his name, but we usually say Kuiper, okay? I'm guessing just the way usually it's pronounced, that would be Kuiper, but we usually say Kuiper. He was born in the Netherlands, Dutch born, but he came to the U.S. and did most of his work in the U.S. So he became an American, but he was born in the Netherlands. He completed his education in the Netherlands, but immigrated to the U.S. in 1933. Does anyone know what was happening around 1933?
Was it the war?
Okay. It was before World War II. What was World War II all about? Okay, stock market crash was right in there too. In fact, that's what sort of precipitated World War II a little bit. But Hitler came to power. Long before we got involved in World War II, he was wreaking havoc in Europe. And I think probably Kuyper, I don't know if he was Jewish, it doesn't say that he was, but he probably wanted to get out of Dodge, okay? And he came to the U.S. We really benefited a lot from Hitler's craziness, because lots of people decided to come get away. Anyone think of another? Second?
I said, what a coincidence.
Oh, yeah. Anyone think of another Jewish guy who came to the U.S. about that time? Maybe a little later than this. Albert Einstein. Okay. His mathematician that he depended a lot, a woman named Emmy Noether, came to the U.S. She was, I think, half Jewish. They were all getting out of there, if they could, to avoid that.
We should go ahead and take the test.
I'm sorry?
We should take the test.
Oh.
Yeah.
No. We're a half hour too soon. Yeah, we got plenty of time. Okay. All right. Let me just review a little bit. So saying here's a good blurb on Gerard Kuyper, Peter Kuyper, or whatever his name is.
It's Kuyper.
It's Kuyper, I know. That's how we pronounce it. Now, this cannot be your source for your paper. If you choose to write on him, you need to get outside source. Not the book, something outside the book. So go find materials outside the book. That's what you use as the sources for your paper. Do not use, this gives you an idea, big idea, okay? If you read this, you may run into some other things. I don't see that many other ones here, but there's several things about several spacecraft. If you want to write about their, there's tons of potential paper topics. All right, and I say this every chapter. I'll say it again, and I'll hope never to forget to say it. Nothing replaces reading the text. Okay? Number one. After you've done that, then using the stuff at the end of the chapters are good things to sharpen up. The summary does focus in on most of the important concepts. Whether they get them all, I doubt it. You just can't get it all in that little summary. The key terms are well worth looking at. Okay? This is a pretty good listing here. They list them alphabetically, but they also list the page number where they first show up or defined, and that gives you a good place to go to look. But then applying the concepts are, in this chapter 41, that's a few fewer than normal, multiple choice questions. Now, I can almost guarantee you none of the test questions will be exactly these multiple choice questions, but some of them may be pretty similar. They may be approached from a different angle, but these will be pretty good representations of what the material is. Huh?
I kind of like these questions.
I do too. They're really good. They have the answers right there. I would go through it without looking at the answers, see how you do, compare it to the answers, figure out the ones you missed, go back and read, find out why you missed it. If you cannot understand why they have an answer different from yours, bring it to class. We'll discuss it in class and see if they got the answer wrong or if perhaps you missed seeing the point. Then there's questions for thought. There's 19 of them in this chapter, which is probably a bit on the heavy side here, but they're really good questions. For further analysis, it's about normal, maybe a little few more than normal. And then the parallel exercises, really, I don't know if they're worth your time to do, but for those of you who are a little more mathematically inclined, you may find them interesting to do. They're good questions. They really are. I won't ask you any like that on the test. Okay. Now, let's talk about what we do next. We're going to barely start chapter 16 now. Okay? And next time, the first hour, 2 hours, the first 2 hours, we will continue in chapter 16. The next 2 hours, we'll have the lab from chapter 15. And then the last half hour, we'll have the test on chapter 15. Okay? They come fast and furious here. Huh? Yeah.
The doctor don't keep you there.
I can't hear you. You want me to go to the doctor? Okay.
Is this Thursday or?
Yes, Thursday. Yeah, we're covering a lot of material in 8 weeks, okay? So this is one of the few weeks we'll have 2 tests in 1 week. Most of the time it'll be about a test a week. Say again?
We have a test Thursday.
We'll have a test Thursday on chapter 15, because we didn't get it finished today. Okay? It'll slow down a little bit, but not much. Okay.
We are having a test on
Yeah.
Thursday.
Today is the test on 14. Thursday will be the test on 15. Okay? All right. We have already finished the lab for 14. We'll do the lab for 15 on Thursday. Now, if we don't get it finished, we'll do like we did today. In the first part, next Tuesday, we'll finish it. I think we'll be able to finish the one on Thursday. It's not quite as long as the one we just did. Okay? But this is a big class, and sometimes it takes a little longer. Okay. So let's at least introduce what we're going to talk about in 16. Now, a little bit more. Again, I mentioned this early in the term, so let me say it again. After 16, okay, this is looking a little bit ahead, we will have a lab for 16. We'll do most of the lab in class as a group like we've been doing. But the last part of the lab, or one part of the lab, you'll actually do at home over about a 2-week period. You're going to be observing the moon. Okay? Yeah. Okay? That's the lab. It's just a little part of the next lab. Not 15 lab, 16 lab. I'm talking in the future. But after we finish the lab for 16, the one that you won't finish it, but we do the one part in class, I will then try to schedule a trip to Sanford, to the planetarium. So that's going to be a nice little break. We may not have a test that day. We'll see. Okay. But that will take up some time. So it'll slow down a little bit. And then we get into the other part, and it'll speed back up some. Okay. All right. So it is sort of fast and furious now, but it's not too bad. So, okay. So chapter 14 was the universe. Chapter 15 was the solar system. Chapter 16 is basically the Earth-Moon system. It's called Earth in Space, but it involves the Earth and Moon. Okay? Then the next group is going to be looking at structure of the Earth and stuff like that. That's geology and that kind of stuff. So here's our core concept. The way the Earth moves in space is used to define time. We've already talked about that some. And describe location on the surface. We've already talked about that some. And causes other recurrent phenomena such as the seasons. And we've talked about that some. We'll go into a little more detail now. Okay? Now this to me is a far better, though it's not perfect, picture of the solar system. They're never all lined up. But frankly, they're never going to be this close together either. But if I understand this correctly, this, I don't even see Mercury, okay? This looks like it could be Venus. There's Earth, there's our moon. This looks like it's taking a picture from the moon back at the other. That, I would guess, would be Mars. You don't see any asteroids in here. That would represent Jupiter, Saturn, Uranus, and Neptune. But still, that's really fantasy. It's not quite correct, but at least it's better than having them all lined up in one thing. And still, the sun isn't really large enough. Okay. But let's first look at the shape and the size of the Earth. This is 16.1. The Earth is not a perfect sphere. We're very close to what they call an oblate spheroid. What in the world does that mean? Well, a spheroid means it's shaped sort of like a sphere. Okay, so that makes sense. Oblate it means it's a little more pear-shaped, slightly pear-shaped. In other words, kind of thick in the middle and thinner. Well, we won't go into that. Okay. Now this I do not understand at all. How can there be a lump in the Pacific? The Pacific is water. If you had a lump in the water, it would flow down, wouldn't it? So I don't quite understand that. And yet they say there's a depression in the Indian Ocean. It seems like there's a depression in the ocean, the water would flow into it. So they don't quite mean it that way. They mean there's sort of like a bump here and a depression there. Okay. I don't like the way they say it, though. There are elevations and depressions of deviation less than 85 meters. Now, what is 85 meters?
What is less than 85 meters?
Yeah. The elevations and depressions of deviations are less than 85 meters. 85 meters would be less than a football field stood on the end. And if you consider the diameter of the Earth to be how many, huge, a football field is nothing, standing on there. And this is not even a full football field. That would be about 90 yards, okay? So no, it's not very major. But we're not perfectly spherical. Now, showing that picture almost looks like you're losing something down here, but what you're losing here is because there it's in the shadow. It's not because it's not. Okay? So this is, again, a very good illustration of it, but it's a very pretty picture of the Earth, taken from one of the spacecraft of the Earth. Maybe from the moon, I don't know. This illustration, again, this is an exaggeration. Okay? The sphere would be the dotted line here. The spheroid, the oblate spheroid, sort of thick in the middle, thinner on the edges. This is the Earth. That would be a perfect sphere. So we're awfully close to a perfect sphere. Again, they've exaggerated here pretty greatly. And what I can't get is rationalizing that to this. Because if you see the difference between these, okay, that difference is 42 kilometers, okay? Well, that's not 85 meters. 42 kilometers would be 4,500 meters, okay, or 45,000 meters. Okay, so I can't rationalize where these numbers come from compared to that. I can't, but this is what they're talking about. It's one of those two, something like 85 kilometers, but 45 kilometers out of 12,000, almost 13,000 kilometers. That's not much, folks. It's a small percent. Again, this is greatly exaggerated the way they drew it. If they drew it reality, they would be almost on top of each other. The dotted line would just be barely past that, barely inside there. So, now, everybody have that, what you needed? Okay. Now let's consider some of the motions of the Earth. Okay? Now, there's another figure in the text, I don't think they show it on the slide, of the solar system, and again they have all these things lined up, but these are relative sizes here. And if you have this, it is pretty incredible. Okay? The closest one to you is Mercury, but it's bigger only because it's closer to you. Then Venus. Venus looks larger than the Earth. Earth is really larger than Venus. Mars looks smaller than Mercury, but it isn't. It's just that it's further away. But these are the relative sizes of the terrestrial planets. If you got this new text and are looking at it, that big blob in the background is Jupiter. See the great red spot? Look how tiny the terrestrial planets are compared to Jupiter. The scale is more correct on this. The placement stinks, but the scale is more correct. Then Saturn is much closer, is huge, but very low density, and then Uranus and Neptune are almost the same sizes. So it's a pretty good picture scale-wise for size, but not scale for distance. But, all right. Let's go to the motions of the Earth. 3 of the Earth's motions are completely independent of the motions of the Sun and the galaxy. Is that signaling me for something? Oh, okay. All right. Okay, good. Okay. I thought, wrap it up, guy, something else. Okay. All right. Are completely independent of the motions of the Sun and the galaxy. So these have nothing to do with the Sun or the galaxy. This is just our motion relative to the Sun. So number 1, we revolve around the Sun. Okay? If this is us, we're going, and a hunter is the Sun, we're going around the Sun like that. At the same time we're going around the Sun, we're spinning on our axis. And we're spinning like, that. So we're going around the Sun and we're spinning. Okay? So that's the second of our motion. It has nothing to do with what the Sun's doing. Now, here's the third one. This happens once a year. This happens once a day. How about this one? Tens of thousands of years before this happens. The Earth actually has a little bit of a wobble in its rotation axis. Not much, very little. What I'm just doing here will take tens of thousands of years to happen. Okay? That's called the clockwise wobble of the rotation axis. Now, what is the effect of that? We're going to talk about it more later. The North Star has always been our North Star. Because we wobble, and the height of our wobble, we're not pointing to the North Star again. We'll point toward Vega sometime. But then, like 10,000 years later, we'll be back at the North Star. Okay? So, not going to happen in our lifetime. Okay? North Star will still be our North Star, our Polaris, as long as we're alive. Maybe as long as mankind's alive. At the rate we're doing, we may destroy ourselves before it ever changes. But they have been able to deduce that. Now, actually, one thing we have seen from this, the zodiac constellations. I don't know if any of you follow that. I don't, so I can barely name them. But those are the ones that occur on the sun's ecliptic. Okay, that circle that's where the sun is. Okay? Some of those that were on the ecliptic back when the Greeks first identified them, they're slightly off of it now, and there are actually other constellations that are closer, but we stay with the original. So that is an effect of that little bit of wobble that's happened over 3,000 years, 4,000, something like that. Okay. Now, what are some of the other motions? Now, these include the ones we were just talking about, but these are the 7 conspicuous motions of the Earth through space. Okay? We rotate at a rate of about 1,670 kilometers per hour at the equator. Now, picture this. We're rotating fairly rapidly, but you see the equator is moving much faster than up here because this is not one. This is going in a day, but this is going several times that much. So at the equator, that's the maximum speed, about 1,670 kilometers per hour, which that would be in miles per hour, about 900 miles an hour. That's going pretty fast. The monthly rotation about the Earth-Moon center of mass. Okay? Now here's something to keep in mind. Why do we have months? Why do we decide to have months? I can see a year because that's when the sun goes from peak to peak. That's in a year. Why do we have months? Say again?
Season.
Okay, seasons, that is from equinox to solstice, equinox to solstice. That would give the seasons. why do we have months?
Lunar cycle.
Okay, lunar cycle. What word do you almost see in month?
Monthly cycle.
Moon.
Which named after
The
the month.
moon in the month, that's what named
Month,
month.
right, month.
Yeah, the lunar cycles,
Right.
exactly. Okay? The monthly rotation about the Earth-Moon center of mass. Remember, our moon is the biggest moon relative to our planet, Earth, as any in the solar system. There are several moons bigger, but they're gas giants. Our moon, so actually our moon going around us, it doesn't do this, it does this. We move a little bit, it moves a lot. Okay? And that one cycle around that center of mass, that's what makes a month a month. The moon, the word month comes from the word moon. Okay? Yearly rotation about the sun. Okay? We're traveling at 106,000 kilometers per hour, which would be about 60 to 70 miles per hour, 1,000 miles an hour. Okay? The orbit of the solar system about the so these this one and this one have nothing to do with the sun or the moon. Okay? This one only has to do with the moon, nothing to do with the sun. This is the orbit of the solar system around the center of the Milky Way. Remember, the center of the Milky Way is that galactic disk, which could show up on today's test, right? Because that was in chapter 14.
Yep.
Galactic disk with the spirals going around it. And we're way out here, about 2/3 of the way out on one of the spirals. So we're going around the center of the Milky Way. We are flying there, okay? The orbit of our solar system around the center of the Milky Way, about 370,000 kilometers per hour, okay? Now, in terms of miles per hour, that would be about 200,000 miles an hour. Flying, okay? Now, our sun is in a local star group, okay? And that orbital motion within the local star group, not in the Milky Way, but within the Milky Way, we're going about 1,000,000 kilometers per hour, which is about 600,000 miles per hour, okay? And then the motion of the Milky Way galaxy relative to remote galaxies, we're going about 580,000 miles per hour from that, which would be about 360,000 miles per hour. And then we have some minor motion, okay? So this 7 actually is more like 9. Minor motions is changes in the shape and size of the Earth's orbit. Now, here's what we mean by that. Can anyone tell me at what time of year we're closest to the Earth, approximately?
Close to the earth.
To the earth.
I mean, closest to the sun. The Earth is closest to the sun.
Summertime.
Huh?
Summertime. Winter.
Actually, we're farther from the Earth, from the sun in summertime. Around July the 4th, 5th, 6th, something like that, we're actually the farthest from the sun we ever get. Not by much, by a little bit.
Not so hot.
And, okay, the reason of that is because we're tilted toward the sun in the summertime. So more direct radiation comes to it, but we're actually a little further from the sun. In the wintertime, we're actually closer to the sun. Now, yeah, think of the poor people in the southern hemisphere. In their summer, they're actually closest to the sun, and in their winter, they're farthest from the sun. So they should have, I don't know if they do, but they should have more extremes in temperatures for the summer and winter. I've never read any data to suggest they found that out, but it would seem like to me that would be the case. It's not a lot of difference. It's a very minor thing. Remember, our orbit is not circular. We're in an elliptical orbit, and we're actually closer in January, and we're farther in July. Not by much, by a little bit. We're close to a circular orbit, not that. The next is a change of the tilt of the Earth's axis. Okay, that's that wobble that we have. That happens over tens of thousands of years. And here's another one, the slowing of the Earth's rotation rate. We're not spinning quite as fast as we were a while ago. Nothing we'll notice in our lifetime and probably in recorded history. But all indication we were spinning faster shortly after our creation than we are now. We are very slowly, minor difference. Very, very slow change there. Okay? The overall picture then, from space, we're not just going around the sun because the sun's going around there. So actually our orbit is like a corkscrew. Okay? We call that a helix. Okay? Here's the description of it. We're going around the sun, but the sun and the whole solar system is going in space too. So we're really doing this kind of motion because we're always staying with the sun there because the sun's moving too. Do we notice that? No. Do we notice going around the sun? No. Do we notice spinning? No. It's only the results that we look at to see. Okay? Viewed from the Earth, though, it looks like the sun is moving. It's not. We are. And that ecliptic plane is the relative motion of the sun to the stars. Okay? See, all these other stars are out here fixed in place, and we're moving around the sun. So sometimes, when we're here and the sun's there, when we're at nighttime, we're looking at the stars that are here. Quarter of a year later, we're over there, we're looking at the stars there. Here we're looking at the stars there, and here we're looking at the stars here. So our night sky changes over the year because we're looking at different portions of the thing. So that explains our eclipsing. That's what stars is the sun eclipsing right now. The stars over here we'll never see at this time of year because we see that's what the sun eclipses them in the day. We'll see the stars over there. Whereas when we get over here, we'll see the stars that we can't see now and won't see the stars over there. That explains the eclipse. The plane of the Earth's orbit around the sun. The planets move in a very narrow band around that ecliptic plane, meaning that our solar system is relatively flat. There are some variations. Remember, Mercury's about 7 degrees off. I think Saturn was about 2.5 degrees off. Venus was 4.5 or something like that. But basically, we're a pancake, okay? With a volt in the middle, that's the sun, okay? Not an even pancake, but a pancake, okay? Pluto, 17 degrees off. Doesn't fit very well. Okay, the sun moves along the ecliptic across the background stars. It really doesn't. It's moving like this. We're moving, and it makes it look like the sun is moving relative to the background stars.
It's 10 after? Or
Yes, I was just going to say this. Okay. I was just going to say we just finished 16.2. Well, we didn't finish it. We're just at revolution. So that's going to be orbit. Okay? If I can find my pencil, this will be a good stopping point right there. Orbit. And we will pick up and go from there on Thursday. That gives you about 3 or 4 minutes if you want to make a quick potty break, water break, caffeine break, any kind of break. Get up and stretch break. Or get your materials out ready for the test. Good time to do that.